Three Java programs here are syntax. Valid. So neither of these has any syntactical errors. However, each of them has context-sensitive violations. So first example, variable a is used but not declared. The second one, f is called with one more argument. The last one, in Java, you simply can't add true and integer together because you're going to see a sort of incompatible type error. So how do you do context-sensitive analysis? So basically there are many ways. You can use some ad hoc techniques. That's the thing done in the past. You can also use some formal techniques. So attribute grammars are just one of the formal approaches. You can specify the process. In this course, we sort of use a mixture of the both. Because VC is very close to C in Java. We expect you understand VC straight away, and we also explain some type rules you're going to use in order to do type checks. So essentially a mixture of sort of informal and formal specifications, otherwise it's just not manageable. Just some more information for you. This is something you're going to see in the second last week. So you can, there are many automatic tools in the compiler area. So instead of writing a scanner by hand, you can specify your tokens using regular expressions that you will see in the second last week. Then you can get a scanner automatically. Similarly, you can also just pass your CFG to a parser generator. You don't have to do anything. The parser generator will just return you a parser. Okay, that's something you're going to see also later in this course. Attributed grammars are here, so that means you can try to build a semantic analyzer automatically. You specify the analysis process by using attributed grammar. Hopefully, you can get a semantic analyzer. The lower you go, the harder it is for the whole process to be automatic. So attributed grammars is just generalization of CFGs because CFGs is not powerful enough. We need to augment the CFGs in order to specify some context-sensitive restrictions. So that's what attributed grammars are. We speak of two types of attributes. You're going to see what these are shortly. So I'm not going to read this for you anymore. Just look at example. So you saw this slide last week. So if we're given G as a CFG, and we would like to augment G by doing something more, like type checking, and you specify all your type rules by using attribute grammar. You define a bunch of attributes. In this particular case, for example, one attribute could be the type of expression. So then you give a bunch of rules, then we can make use of the rules just to build a type checker for you. The last bullet point is something you understand very quickly. So when you define all these rules, each of these rules will be associated with a production. And you define a rule to compute the attribute by using other attributes. But all these attributes must be related to that particular production. Okay? You will see this shortly, don't worry about it. But now you should have been familiar with the style I do my lectures. A few formal slides, and later on we have examples. When you see the examples, everything will be clear. Okay? We'll come back to this last point of this example. Attributes. What are the attributes? It really depends on what you do. Attributes can be anything. It can be string, number type, a sequence of code, instructions, so on and so forth. Well, given all this, we're going to see the first example. Okay? Here is the first example. So on the very top, you see a grammar with 4 productions, 2 non-terminals and 2 tokens. Okay? Number in the second last line just defines integer, and number in the last line just defines floating point number. This grammar is ambiguous. However, it is okay now to use an ambiguous grammar to define our attributed grammar. The reason being that the parser has already been written. For example, if you want to write a parser to parse this language, you would have started with another grammar which defines exactly the same language as this, that gives you a tree representative. After that, you can use an ambiguous grammar that is equivalent to the non-ambiguous grammar, so that it makes it easier for you to specify your rules. Okay, here are the restrictions. Because it is ambiguous, then when you are giving one expression, you may find 2 different trees. Now, since we have these restrictions, and the grammar becomes non-ambiguous now. We say division operator is left associative. So that means every time you see this, you must perform the first division first. Otherwise, you don't know. So because of this restriction, the grammar becomes non-ambiguous. In addition, all the mixed expressions must be promoted to floating point expressions. So what that means is, you saw that example here. In Java evaluates this expression differently, always from left to the right. Okay? So you have an integer division, and you have a floating point division. That's why you get 1.0. However, we don't want that semantics. We want different types of semantics. Okay? What we are saying here is that if we are giving this expression, as long as there is a single floating point value inside that expression, all the divisions must be done using floating point division operator. So that means you scan the entire expression, then you realize the last one is 2.0. Therefore, both divisions must be performed using floating point division operator. Therefore, you get 1.25 instead of 1.0. Because when you divide 5 by 2, using the floating point division, you get 2.5. Then divide half that again, then you get 1.25. Okay? So that is the grammar. So our task here is, can you formally specify this evaluation process using an attributed grammar? So essentially, what I have explained to you is very informal. Suppose you would like to formally define how this expression is evaluated, but you are lazy, you don't want to write that semantic analyzer, you want to pass that to somebody else. Okay, how do you communicate between you and that somebody else? Okay, you need to pass that guy a formal specification for that. Okay? So you can do that by using a so-called attributed grammar. Okay, this stage, of course, people don't have really a clear idea what is going on here. It's just, let's go through all this just in today's lecture. So on the left-hand side, you see 5 productions. As you can see, every terminal, every non-terminal is now associated with some attribute. For example, we say expression dot type. So obviously that means this expression is going to have a type. Okay. Then expression dot val, that means that guy is going to be evaluated into a value. Okay. You also see something like expression dot is a float. So essentially we are checking to see whether that expression contains a floating point value or not. Whether all the divisions should be done using floating point division. You see 3 attributes. Now you have to figure out a way of specifying this evaluation process. That means as long as there is a single floating point value, then all the divisions should be done using floating point division. Okay, it's not that easy. Then you have to use these many rules. Okay, so with 3 attributes. Now, what does this say? What this means is, if you look at each of these rules, okay, just for example, take just this rule on the very top, okay, when you define how to compute expression.type, we are only allowed to refer to the attributes either here or there, but nothing. That means every time I try to compute an attribute here or there for any of these things, you are only allowed to use attributes associated with the non-terminals in that production. In other words, if you consider every production as just a function, we are only allowed to use local variables. Okay, we cannot use global variables. Now you might ask, what if we want to use information from another production? You just have to pass it around. Because imagine you are asked to write a Java program without using global variables. What are you going to do? You just have to pass information around using parameters, global variables. Obviously, you can do that. Okay. Why do people make this restriction? Just to make sure people don't make mistakes. Once you have too many global dependencies, it's sometimes hard to manage. Okay. Still, we have no idea what is going on. However, if we divide these rules into 3 subsets, things will become more clear. Now we look at the first 3 rules. Is float. So what does is float mean? That means every expression is associated with attribute called is float. What we are, this is a Boolean variable. We set that attribute to true if that expression contains at least one floating point value. Or you say if that expression is a floating point expression. Because the expression is a floating point expression, if and only it contains at least a single floating point value. Now it's not very difficult to understand. For example, if you are given a single integer, obviously that's false, because a single integer is not floating point expression. A single floating point value, of course, is true, because that itself is a floating point expression. Now, this should not be surprising. We want to see whether that guy contains any floating point values or not. Well, as long as one of these two contains one, that guy has to be set to true. That's why you see it's all. Right? So that's 3 rules for us to decide whether an expression contains any floating point values or not. Once we have done that, whether we know whether the expression contains any floating point value or not, we can give a type to that expression. Okay? That's not very hard. For example, we say, if you are a floating point expression, then your type must be float. Because when we evaluate this expression, we get a floating point value. Otherwise, we're going to get integer value. Okay? Now here, we look at the guy on the left-hand side, the parent. If you are type, whatever you are type, the children will have the same type. Well, that should be obvious, because if the large expressions are typed float, then anything else, any sub-expressions must be typed floats. That's because of the requirement that as long as you see any floating point value, every sub-expression must be a floating point expression. So it's also fairly simple. Now we know the types for all the expressions. Now we can evaluate all the expressions on the tree. That's not very difficult now. Every time we say a number, what do? Then we say, okay, we have a number. What is your type? If this guy's type is integer, just return an integer. If that guy's is typed float, you have to return a floating point representation. So this float is a function that converts an integer to its floating point representation. Obviously, this is that. Here is simple. You simply just check to see what is the type of this expression. If it's an integer expression, you use integer division, otherwise you use a floating point. Now if you evaluate all these rules, you're going to, yes. Which one? You mean this one? Why? Because this is, you will see later I'm going to do a good test how these rules are evaluated. Because if you see an individual number, you have no idea where this number appears in a large expression. For example, you're going to see this soon. If you see this number 2 alone, you don't know whether you should treat that as a 2 or 2.0. You will see that clearly later. Okay, understand what you're asking. Because his question is, since we know it's integer, why don't we just say integer? You can't. You can see this clearly just in a few minutes. So if stands for integer division, this is a floating point division. It's just a function that converts integer to a floating point value. You can treat now.var as a token returned from the scanner. Okay, now we talk about two types of attributes. So we say isFloat is a synthesized attribute, is defined over this domain, because isFloat is a Boolean variable, and type is inherited. And synthesized, the var itself is also synthesized. Okay, because see a few slides soon. And once we are given an attribute grammar, we can always work on the dependency. For example, we see this as a dependency. Why? If you look at this attribute grammar here, firstly you have to evaluate the attribute for this flow, because we need to know this in order to know the type. Certainly there is a dependency here. We say the type depends on its flow. Firstly, you need to compute its flow, then you can compute the type. And here, we need to know the type in order to do the evaluation. Certainly, you can deduce the dependencies among the string attribute in that sense. In the sense that, firstly, you have to compute its float, then you compute the type, finally you compute the var, otherwise it's not going to work. Okay. So, what are synthesized and inherited attributes? A few slides will make all this clear. Again, we need to look at how we use this attribute grammar to evaluate the given expression. If that is the given expression, this will be the unique tree we are going to construct. That's because the division operator is a left associative. Okay, this is the only tree because the first division will be done first. Okay, once we're given that tree, we can apply the rule to evaluate, compute all the attributes. Now, if you just evaluate all those rules by respecting the dependencies, that's eventually what you're going to get. Okay? Eventually you're going to get 1.25 on the very top. Now, at this stage, you might see a little bit why we need to convert this to 2.0, because everything has to be done in floating point divisions. Now, this looks like great. But how? Okay? Remember there is a dependency. 3 attributes? Yes. To use float, we need to do a sort of examination of the whole expression inside out to determine whether the entire expression contains any floating point value or not. So you need to scan the entire expression. You want to know whether every expression, basically if you want to know the type of any expression, that's something you got to do. I mean, pretty much that's something you have to do. Well, you would pretty much do the same thing. For example, how do you know the type of this guy? That means you have to do a traversal on the tree. Eventually you figure out that there is 2.0, then you can set this guy's type to the flow. Otherwise you wouldn't know. But conceptually, that's the process you have to go through. You understand that. Yeah. So now if we split this into 3 slides, then things will become more clear. Firstly, conceptually, we need to compute isFloat for all the expressions. We need to decide whether any expression node on the tree contains a floating point value or not. So we do that. If you can see the red arrows, isFloat, we say isFloat is a synthesized attribute, because if we want to compute isFloat attribute at a node, we only use the attributes from its 2 children. Okay, so look at the rules again. We compute isFloat attribute at the parent node by using isFloat attributes at its 2 children. Okay, let me back to this slide. So essentially we do a post-order traversal. Here we see a file. We say, what is the value for isFloat? Because this is an integer, certainly it doesn't contain any floating point value, it's false. In post-order traversal, we are here. Again, 2 is not a floating point expression, it's set to false. Now, here, we know the isFloat attribute at each of the 2 children. Now we can apply this rule here, to set isFloat attribute at the parent. Here, in a post-order traversal will be here. 2.0 is a floating point value. obviously, its float attribute is set to true, because this guy is false, that guy is true. If you apply this rule again, we have to set its float attribute to the whole expression to true. Okay? Just to set differently, its float attribute expression node indicates whether that expression contains any floating point value or not. Okay? Obviously, it's synthesized because if you know this property at each of its children, then you should be able to deduce the same property at the parent node. Okay? Just by adding all these float attribute values together. So that's how we compute this float. It's called synthesized because you always compute that by using the values from its children. Now, if you look how we compute the type, it's the other way around. Okay? Since if you look at the rules again, you should be able to deduce the same property as the parent node. Okay? Just by adding all these float attribute values together. So that's how we compute this float. It's called synthesized because you always compute that by using the values from its children. Now, if you look how we compute the type, it's the other way around. Okay? Since if you look at the rules again, only two rules. If we know the entire expression is a floating point expression, we set that expression to float. Otherwise, we set that to int. Once we know the whole expression is int, then each of its sub-expression will be. If that entire expression is a float, then each of its sub-expression will be float. Okay. So as you can see, we simply propagate information from the parent to its two children. So that's what we do. Since the whole expression is typed float, then we simply just propagate the information all the way to their children by applying the second one. Now we know. Any other questions? Yeah. Yeah, you can use any. It's just an attribute. You can name it any way you like. Well, it's always an attribute. As we said, we are not allowed to use any global. You can't use global values because we're talking about an attribute for a particular node on the tree. Yeah, we basically you have to think recursively. Here we're talking about right now. We are really talking about sub-expression 5/2. What is this? What is this guy's type? Here we're looking at the type of sub-expression 5. This 5 is typed float, not integer in our semantics, because we're dealing with so-called mixed mode expression. As long as there is a single float anywhere else, everything will be floating point divisions. That's why you see 5 is typed float instead of integer. That also answers your question, the question you asked before. Right? So finally, yes. A good question. His question is, what if you end up writing rules, you end up with cyclic dependency? That would be wrong, because you're not allowed to have a bunch of rules that give you cyclic dependencies, because you can't evaluate them. Okay. So essentially, the dependencies will be part of all that. So you can always figure out the way of evaluating that. So it's just, just the whole thing is sort of new, but eventually you're going to see it's not very difficult to evaluate everything. But now you see we know the type. Then we have the last attribute is called val. This guy is synthesized because we evaluate everything bottom up. Okay? So now we see this is 5, its value is 5.0 by applying the rules. I'm going to go through this again, okay? So here we need to do a floating point division according to the rules. Okay, again, I'm going to go through this example in a few minutes. So eventually you get 1.25. But the point here to remember is this third attribute is also synthesized because when you evaluate any expression at a node, you make use of only the values from its two true. Okay? So you synthesize things in a way. Okay? So in general, I'm going to explain this slide here. Maybe it's better if I draw it here. So what we are saying here, suppose we have a production. X0 derives x1, x2, xn. So essentially, you have already done a assignment. So if you build a tree, pretty much that's what you get. xi. What do you get? Xn. Okay. So if this is the production given, x0 derives x1 all the way to xn, that means in the tree you have n children, x1, x2, the third one is xi, and xn. So in general, what are synthesized and inherited attributes? Okay. This one says, if you want to compute an attribute at the parent node called syn, you can use all the attributes from these guys' children. Okay. So this ax1 just means a bunch of attributes you can find it from the children. This is saying is, if you want to compute something here, okay, you can feel free to use any of the attributes from his children. This guy is called synthesized. Essentially, you make use of the information from the children to compute that attribute at the parent node. On the other hand, if you want to compute an attribute at this xi node, now if you use attributes from here, attributes from here, attributes from here, from the siblings, either on the left, on the right, or from the parent, that's called inherited. It's like you inherit something from your parent. Here, by definition, you inherit something from your sibling nodes. Okay? That's called inherited. That's it. This is just by definition. Essentially, if you computing the one attribute at a parent node, if you use only the information from its children, that's called synthesized. Otherwise, it's called inherited. Yeah, I will get back to you soon. So if you look at these two examples, this is synthesized because information flows bottom up. This guy is also synthesized, but the second attribute is inherited because every node inherits the same type of information from its parent. So information just goes from top to the bottom. Okay. What's your question? Yes, because in terms of writing a semantic rule, we are only allowed to use attributes the same production. Any other questions? So far, so good? Okay. So, it's just, I think you need to work out a few small examples to fully get this. Now, once we are given an attribute grammar, which consists of a bunch of rules for computing attributes in terms of attributes, how do we evaluate a given set of attribute rules? Right, you have already seen me doing that. Is there a systematic approach of doing that? Yes. The first one is very simple. It's called tree walking algorithm. So you build a tree representation for your input for the expression. You walk the tree from the root towards the leaves. By doing pre and post order traversals, now you can evaluate any given attribute grammar. As you can see here, as long as the attributed grammar is not circular. That means you cannot have circular dependencies. If you have circular dependencies, that means that attributed grammar is not well formed. It's wrong. It's incorrect. Okay. So there are two ways of doing that. We look at the second one tomorrow. Today we just look at the first simple approach. How do you do that? Very simple. Here's the algorithm. It says you have a while loop. It says I'm giving a set of rules. As long as there are some attributes that are remain to be computed, I have to keep doing that. What do? I call visit node from the root of it. So as long as there are attributes I need to evaluate, I call visit node from the start, from the root of it. Here we call this guy. Now if you look at this algorithm, all these algorithms is doing is to perform a pre-order and in pre-order and post-order traversal. Okay? So every time before this guy is just about to visit one of the children, it's going to check to see whether there is any inherited attribute you can evaluate. As you visit a node, just before you visit a child, you're going to look through all the rules to see, hey, is there any way I can apply to compute one more or two inherited attributes? At this point, once you have visited all the children for this guy, this guy has m children. Once you visited all the children, you're going to try to see whether you can compute any possible essential size attribute at the parent node. Okay, so essentially you do pre and post-order traversals together. During the pre-order traversal, you apply rules to compute inherited attributes. When you do the post-order traversal, you try all the possibilities to compute as many synthesized attributes as possible. That's it. Okay, if I give you a demonstration, it should not be hard to understand. Here, we can do it here. So this is that example, 5/2/4.2. Okay, so we're going to see how we can apply this rule. Right? Let's say we have no idea in which order we're going to apply that. It's just a bunch of rules. We don't care how they are related. But of course, we have to understand the dependencies. Okay? So we, according to the algorithm, it says as long as the attributes that need to be computed, you just have to do that first. Guys, we have to start it. We haven't started yet. Okay, we call visit the node starting from here. Okay, so there is attribute. So now you got to look at algorithm. And obviously, you cannot do this because you have no idea about because in order to compute this guy, you have to know the value of this guy. Okay? Then you do your pre-order traversal here. Now again, there are three attributes because this is expression node. This is expression node, that's expression. Okay, because we only have expression node. The root is S node, that's it. Okay? So at this point, of course, you want to see whether you can compute type var of each node. There's nothing you can do. You can look at all the rules here, because if, for example, if you want to compute the expression dot type, okay, and there's no rule you can apply. Okay, so basically, you traverse the tree all the way until here, until the first leaf node. This is the point, because this guy has just one child. Just before you return to the parent node, because you're doing a post-order traversal now, you want to see whether any synthesized attribute here can be evaluated. Well, look at this rule. This rule does not have any dependencies. It says, as soon as you see a number, integer, you set it to false, because it's not written by expression. Okay? So,
Are you using Oculus? That's my guard. Seems like Oculus, not Oculus.
I never used this tool before. Maybe there's some
Bruh, he's got a whole drawing tablet
this
right
first
here.
time I just installed this PDF annotator. So basically, once we're here, we check to see whether there is a synthesizer attribute. You can evaluate. Obviously, you can do that because, as I mentioned here, this rule has no dependencies. You can apply that. Now you're doing post-order traversal here. Within this node, this guy has one child. Once that is done, and look at the algorithm. At this particular point, you need to see whether you can evaluate any synthesizer attribute at the parent node. So this is a parent node. We can do it. Again, it's easier. We set that to false. Now, we have visited these two children. Now getting back to the parent. That's the time for you to check to see whether you can evaluate any synthesizer attribute. There are only two synthesizer attributes. One is float, other one is val. Only these guys can be evaluated. Now you look at the rules. We can apply this rule. Okay? When we apply that rule, we got, so that is false. Now we're doing first order traversal, we can see a floating point value, and we can apply this rule because there's a floating point number. So that's true. Now we are going to come back to this guy again. There's a chance to apply this rule one more time. Because one is false, other one is true. If you look at the rule, it's all. So that is true. So now we're going back to the root, and we look at whether this guy can be evaluated. The answer is no. Okay. So we start from the root. We do a pre and a post order traversals implementation. And by doing traversal tree just one time, we have managed to evaluate one synthesized attribute. That's actually demonstrated here.
So you have to go through it again.
Right? Now, if we look at the algorithm, we're back to here. So essentially, we'll call this guy once. We successfully evaluated one single synthesized attribute. There's a loop here saying if you have more attributes to do, you still have to do exactly the same thing. Now we call this guy again. Then we are basically starting from the root angle. There's nothing we can do here. Now we look at here. Remember, every time before you visit a child node, you need to check to see whether any inherited attribute you can evaluate. Now, if we look at this guy, it says we can evaluate this inherited attribute. Because if we know this value, we know that. Right? So obviously, we know this one is true. Then we set this type to true. Snap or something. So this type is a flow. We can copy this type information all the way from here, and now we are here. Okay. Once we are here, before we go back, we need to check to see whether any synthesized attribute we can evaluate. Remember here there is a bar. Now we just look at this guy. This guy says if the type is integer, we simply set that value to an integer value, otherwise we set to a floating point. As you can see, the type is a floating point, is a float. So we essentially write here 5. Right. 510.
Is Oculus that bad? I don't even have Oculus.
So we just, sorry, it's kind of easy. essentially we set this one to 5.0 because we need to do a floating point conversion. Then we are going to visit this node. Okay. Now, since we are going to traverse this right child from here, then we need to evaluate this inherited attribute. And these two rules can be used. We simply just propagate this type information from the parent to this right child. At this point, we can also evaluate this val because we know its type is a float. So we need to set this to 2.0. So this is 5.0, 2.0. Now we are back to the parent. So once we are back to the parent, we can also decide to see whether this synthesized attribute can be evaluated. Now we can apply this rule. Because we know the type is float, we need to do a floating point division. So we get 2. Now we get 2. We get 2.5 here. Okay, I can write that. So we get 2.5, but you get the idea. Now we're going to visit this guy. Now before we do that, we need to propagate this type of information to here. So let's float again. Again, this one can be evaluated. Now we know this guy is just 2.0. Obviously, 2.0. So finally, we are back to this guy. Again, you can apply this rule one more time since we're going to use floating point division. 2.5 divided by 2.0, you get 1.25. Now we are back to here. We just apply this rule. Now you get 1.25. Okay. So I think you get the idea. Sorry for this to never use this before. Let's coming back to.
Is ocular meant to be that bad? I'm not going to download ocular test.
This will make more sense to you. So basically, you apply this so-called pre-working algorithm, and you repeatedly traverse the tree, trying to evaluate synthesize the inherited attributes. We have traversed the three clouds. In the first traversal, we managed to evaluate this float attribute. In the second traversal, we managed to evaluate both type and val at the same time. During the post-order traversal, we evaluate the val. During the pre-order traversal, we evaluate type. So this means that even though we have 3 different attributes, we might use less than 3 passes to evaluate all the 3 attributes. Is this clear now? Okay, good. There is actually so much I want to say about the first example, but this today lecture is not very long, but I'm going to talk about some and 2 of these. We're not going to have a break today, we can finish it early. Okay, just coming back to this animation, you can try yourself at home. I need to fix this issue today. So basically, you apply the working algorithm. During the post-order traversal, you try to evaluate as many synthesized attributes as possible. During the pre-order traversal, you evaluate as many inherited attributes as possible. Eventually, after a few number of passes on the tree, you're guaranteed to finish evaluating all the attributes. Reason being that the attribute grammar is not circular. Because as long as it's not circular, in every traversal, I think I made some comments here. Suppose you have an attribute. In every traversal, you must evaluate this one. Okay, so then the number of attributes that remain to be evaluated will become less and less. When you do more and more traversals, and more and more attributes will be evaluated, and eventually the algorithm will come in at all the attributes will be evaluated.
Why is it on squared? Oh yeah, okay. That kind of makes sense.
So there's guaranteed combination here. There's no problem. Okay, any questions? Yes. Well, it depends. For example, if we're talking about this guy, okay, so tomorrow you're going to see, at the beginning of this lecture, I mentioned there are two special categories of attributed grammars. One is S attributed grammars. We're going to talk about it tomorrow. The answer is very simple. You have attributed grammar in which all the attributes are synthesized. So attributed grammar is another special case in which, that's related to your question, when you try to evaluate inherited attribute at a node, you are only allowed to use attributes in the siblings sitting on the left and attributes on the parent node. You're not allowed to use attributes from the sibling on the right. Then that gives you a special class of attribute grammar. However, in the most general case, as long as there are no cyclic or circular dependencies, you can freely use attributes from any node on your left, on the right, because of the absence of circular dependencies. Eventually, you will finish evaluating all the rules. So that means right here you can use attributes here is available, you can use attributes here available. Even if it's not available, you don't do it now, but in the next one, that guy might become available. Now you can use it. For example, to evaluate this guy, you might use attribute here, maybe called ABC, it doesn't matter. But even though this particular traversal, ABC is not available yet, but in the next one it might be available. Now you can evaluate this guy, if you really have to use that to compute this one. Because you don't have circular dependencies and algorithm working there. Yeah. But yes, of course. I mean, if you have that sort of attributed grammars, it might take more time. So that means you should try to design your rules so that they can be more efficiently evaluated. So yes. Yeah. Any other questions? All right. So we're going to talk about the assignment 2. For assignment 2, there's not much to say for assignment 2. So remember, assignment 2 is part of the larger assignment in which you're going to implement a parser. This is really just the first stage. It's called a recognizer. I don't know why some students still confused. It's called a recognizer in language theory. A recognizer is like a decision-making software that simply answers yes or no. Okay, yes if it's legal, no if it's not legal. It doesn't care about the error recovery. That's why I'm going to say something about that after this. Okay, as long as if it's technically valid, you print 1, otherwise you print 0. In our case, 1 means compilation was successful, 0 means compilation was unsuccessful. We simply just compare your output with ours in terms of this keyword, successful or unsuccessful. We don't really care about the error messages. So if your recognizer has bugs, you might download the test cases we used for marking assignment. Now you can fix all those bugs so they can move on. Obviously, we're not going to give you any reference solution because it's just the first stage of this assignment. You're going to move on to extend that to get a passer. Okay. What I want to say, because I don't have much feedback for this, because you must have realized by now, recursive design parsing is conceptually simple. You build first follow sets, then you build the select sets for each production, and you just do that. And for real world programming languages, first follow sets are very straightforward to compute. And once you've done that, you get a parser straight away. Some student solutions fail on test cases because they didn't compute the first sets or follow sets correctly in some cases. But in general, you can see over 80% getting HDs, THDs. So any queries on the assignment before I talk about errors, how to handle errors in a few minutes. All right, so this. Okay. Some students have asked me, just out of curiosity, how do we do errors? How do we deal with errors? When you deal with errors in a production compiler, there are three issues you have to deal with: detection, recovery, and reporting. Firstly, you need to detect errors. Secondly, you want to report error as accurately as possible. I'm sure a lot of you must have some beta experience dealing with error messages from languages like C++. Some error messages are not that easy to understand. What that means is that it's not that easy to give error messages accurately. A lot of error messages don't make any sense. So you've got to detect errors, report errors accurately. You try to recover from error so that you can keep going. In our implementation, we use the panic mode sort of approach. As soon as we encounter the first error, we just stop. Some students say, how do we do it in general? In general, it's almost like you have written an article in English. I have some grammatical issues, maybe you're not, like me, we're not native. You want some sort of native English speakers to polish your English. And suddenly, if you give your article to 3 different people, you'll come back with 3 different revised versions. They even will fix, for one person, there might be 10 grammatical issues. For another, it could be just 5, because the moment you fix one, some other will disappear. Okay? But how do you recover from errors? How do you revise somebody's article? You can add a word, delete a word, delete the entire paragraph, add a new paragraph, rephrasing a few sentences. The real-world production compiler will do the same thing. Right? So I just want to show you when. So if you look at the grammar for VC. Okay, so let's look at one example. So let's say we just create a test case. You have 1 plus, stuff like that. You might have more statements following that. So obviously here there's empty, terrible parentheses, and in our current implementation, we can stop right there. We see the left parentheses, we want to see an integer, then we just stop, right? So if we look at on our current so, it prints something illegal, primary expressions and stuff, not readable. Now, one of the error recovery approach is to enrich or modify your grammar by adding so-called error productions. If you look at the productions defining primary expressions, we have 7 possibilities. Look at this one. According to our grammar, every time you have a pair of parentheses, you must have a non-empty expression inside. So one possible strategy for recovering from errors is to add a so-called error productions. In this case, we could just say we add this production as as the eighth alternative. Okay? See, we have this, we just add another one, saying, okay, that's also accepted, except it's an error production. Whenever this guy is applied, I'm going to print error message. So if that's the case, then we can just rewrite our implementation of the corresponding passing method for that. So here we go. See, here, if we see the left parentheses, we accept that, we call pass expression. Now we have added a new production. Then we can say, okay, there's another alternative, is the left parentheses, we check to see if we see immediately a right parenthesis. Okay. If that's the case, oh, by the way, so there is a method that's not used, but don't ask me why this called a report restriction. I just modified this a little bit. I just added this line saying, whenever I see error message, I'm going to report that. I increment the number of errors by 1, but I don't stop. Okay, so I'm going to call that. So basically say, so if I see left parentheses, then immediately right parentheses. So I don't know why I call error restriction. You might just say, I don't know, it's arbitrary, some arbitrary error message. So if I see these two together, I'm going to print error message. Otherwise, I want to see expression. Okay, so yeah, so that's it. So in the exam part, I'm applying this production. Okay, so when I apply that production, I report error. Obviously, current token is still pointing to right parenthesis. Otherwise, I'm going to call pass expression. I'm going to apply this production. And finally, of course, I want these two parentheses to match. So if I do that, see, obviously the production is applied, I print something more meaningful, and obviously more things can be the recombinite that keeps going. To see that, I can just delete that one. That means the third line is also syntactically invalid. Obviously, it's going to report the error because once this is empty parentheses, it just keeps going. They report the next error, then it stops again. But anyway, I'm just telling you one of the ways of recovering from errors is just to add so-called error protection. How do you add that? It's art. It's not science. An experienced developer will decide where to add appropriate error protections depending on how they perceive the sort of mistakes the developer are going to make. Okay, this is one way. So we have done that. Just maybe just more so fine. So let's say, of course, in the first assignment, this is not legal because continue has to be inside a for loop, a loop. However, syntactically, this is syntactically correct. Okay. Now, if we don't have a semicolon, and if we run this, as you can see, we can see an error message saying we want to see a semicolon. Okay. So here, so we can also do some sort of error recovery here. We can say, okay, after we have seen continue, we want a semicolon. So what if it's not semicolon? Okay. So now you can just say if current looping not. If it's not semicolon, so you say, okay, after continue with the semicolon, it says it's not semicolon, I just report error. Something like that. So that means is essentially you are inserting a missing semicolon. So if it's not semicolon, I report error. I pretty much assume that's match. Okay. Then otherwise, you just call match to match that. So that's sort of one way of doing that. So as you can see here, in this case, since there's a missing semicolon, we effectively have inserted that semicolon so that the parsing can continue. Okay. So idea here is that during the parsing process, the compiler developers will anticipate some sort of a, syntactic elements that programmers tend to forget, like semicolon, that might be inserted. As you can see, this is not fantasy. When you insert things, that might cause some other errors. Okay. Alternatively, if you don't see a semicolon, instead of inserting it, you can also start skipping tokens until you see the next semicolon. You can do that too. You can just say, if it's not a semicolon, you want to see that, you report that, now you say skipping until you see a semicolon. So what you're going to do is so if it's not so basically what we are doing is after continue we want to see a semicolon. If it's not a semicolon, we report error. Then we enter into the while loop. Then we insist to see a semicolon before we stop. Okay, you can do that too. Oops, it's not good. So now, if we change this example a little bit, so after continue, we put a lot of rubbish there. After continue, we want to say semicolon. Since it's not semicolon, this guy will print error message and say, I want to say semicolon. I just keep skipping until you see one. Okay.
The heck is going on? I'm not listening.
So that's basically what it's doing. This is, when it's processing this guy, it sees this, and just keeps going. To see whether it keeps going or not, let's delete that. Okay. Obviously, it's going to report error there as well. Okay. Because it just keeps going until you move to the next sentence. Now, in general, what's the philosophy behind this? So remember these are pass statement list. So according to our grammar, statement list gives you a list of statements. So here you're going to, call pass statement. Then inside pass statement, we're going to call pass if statement, pass while statement, so on and so forth. Okay. Let's say whenever we have some while statement, but it's very buggy, a lot of spaghetti code here. It's just a lot of rubbish. After that, you have while. So at a certain stage, when you call pass statement list is going to pass statement. I'm sure you remember now because you have something to be marked. The pass statement is going to call pass if statement, pass while, pass for, whatever. Suppose pass if statement has been called. And this guy realizes, hey, it's just spaghetti code, it's not if statement. So what this guy can do is, as I demonstrated earlier, just skip everything until it says something that can legally begin the next statement. So this is where the concept of follow set is. So that means, let's say you ask me to check to see if it's an if statement. I see a lot of grammatical errors, I'm sick of it, I don't want to do anything. Okay? I just skip everything until something that can follow a statement. Or that obviously means that can begin a statement. So that's the exact concept of the follow set. They just compute the follow set of statements. What can follow a statement? While or for or that. So essentially you skip until you see for, if, while, anything that's in the follow set of a statement. Then you return. Okay? You are pretty much fooling the caller by saying, look, everything's fine. That guy will just keep going. So that's pretty much the idea. Why did not ask you to do assignment on this? Many reasons. Number one, we got 10 weeks. We don't have time for six assignments. Secondly, how are you going to market? Different people are going to do it differently. There's no way to say which is more correct than others. We all have pretty different error messages. You could just print 2, this guy could print 100, you can keep skipping, that guy can keep inserting, there's no way you can mark all these sort of assignments eventually, as long as you do something, everybody will get full marks. So the basic idea behind this is very simple. Okay, hopefully get this idea across. Yeah.
Bro, move down.
Yeah. You need when you scale. It's difficult. For example, it's very difficult if you sort of understand the intricacies of error recovery. It's almost like, as I said, if I'm given an article to revise, the article is full of grammatical errors. You can revise very differently. You can just throw away an entire paragraph, which might contain 10 grammatical errors. You might simply just say, this is just too messy. There's too many errors. In any case, if you want more information, you can see the link I posted to the forum. So the basic idea is just make use of first follow size, error corrections. Again, different people do it differently. I didn't fully understand what you say. For example, you might have, remember the example we had before? So, I mean, if you have that sort of assignment, you should have to guess what the original intention is. The programmer might mean this. You might just print error message saying, hey, your floating point number, this doesn't have a legal format. What if the guy means this? Maybe it's something else missing. How do you know? You really don't know. Okay. So essentially, it's a sort of strategy you have to incorporate into implementation. That's why eventually, if you look at the C++ compiler, after a few meaningful messages, a lot of error messages are just not static. So I don't know how you guys work. I know what to do with your first field and fix when I start recompiling the code. Because a lot of our letter messages just don't make any sense. All right. Any questions? Okay. So I see you tomorrow then. So we have another lecture on attribute programs tomorrow.
I did not listen for the second half of that. Wait, so what was he talking about?
So essentially, it's a sort of strategy you have to incorporate into implementation. That's why eventually. Yeah. We'll see if it's that. I see a lot of grammatical errors. I'm sick of it. I don't want to do it. Okay. Remember the example we had before?
It doesn't matter. I think that's the same person.
was redone. If somebody watches lecture recordings, they can just let that be available from our course page. Okay, so we're going to continue from where we stopped yesterday. So I mentioned, so we had a look at the attribute grammars. The whole idea is just really just use a very small example to understand what attribute grammars are, the basic ideas behind this approach. Two types of attributes. The key elements, when you define your attribute grammar, you have to have attributes. You need to design a set of rules by which you can compute one attribute by using other attributes. And as long as your grammar is not a cyclic, it's not a circular in the sense that as long as it does not have any cyclic dependencies, you can always find a way to evaluate all the attributes. There are two ways of doing that. And the one we looked at yesterday is sort of the simplest approach. You simply just walk through the tree, starting from the root of the tree, and every time you combine your pre and post-order traversals, you try to evaluate inherited attributes during your pre-order traversal. Now you evaluate as many synthesized attributes as possible during your post-order traversal, and eventually you should be able to evaluate all the rules and compute all the attributes. Today we're going to look at a second approach. That's the approach we're going to use in the last two assignments. Because yesterday somebody also asked that question. What's the point of traversing like a crazy, from the top to the bottom in many rounds? And if you take a look at the attribute grammar, you might realize, this can be done in two passes. Then just a fixed order, you can fix the order in which you evaluate all the rules, you can do it more efficiently. That's what we call rule-based. It's typically used in compilers. Now we will have a look at the visitor design pattern. I will spend just really very short amount of time on that, because everybody will understand that, because you got to use it in your last two assignments. Three examples. We're going to continue looking at the first example. That's the example that requires us to specify how to evaluate mixed mode expressions by using attribute grammar. So we did that yesterday. At the end of today's lecture, we're going to spend only a few minutes looking at the other two examples because they are fairly straightforward. So, in order to demonstrate how we do that, we're going to see how we can write a parser. Obviously, we're not going to spend time on that. As you can see, all the lectures are sort of integrated in this way. You're working on developing a parser. And these few slides also show you how you can write a parser. For the CFG given yesterday, we cannot use that one because that CFG is ambiguous. If you want to write a parser, we have to use a slightly more complex grammar, as you can see, and with more non-terminals. We need to have more terminals because we want to make sure the division operator is left associative. Yesterday, the grammar is simpler, but the grammar itself cannot tell us whether the division is left or right associative. You have to add one more comment saying that operator is left associative. And here, we use a slightly more complex grammar that precisely enforces that restriction. However, you cannot write a top-down parser by using the initial grammar. It has left recursive productions. So you proceed to eliminate that left recursion by using, for example, this cleaning closure with the star in the bottom of the slide. Now you can proceed to write parser for that. Now, remember, in order to write parser, we need to build an abstract syntax tree. So Java is an OO language. You can see how it facilitates a code reuse. If I want to write a parser for this small example, I just copy, this many AST classes from the AST directory because we have a lot. I only need this field, so I just grab them. I have to, as you can see, it's a class hierarchy. AST is the topmost class, which is the subclass of everybody else. If you look at the indentation, that gives you the inheritance relationship. Okay, so S is the subclass of ASD, and that's pretty much what we did before. Anything that's prefixed by plus is before is abstract. Anything prefixed by equal sign is a concrete. So same as before, we added a new ASD class called S because that's what our start terminal is. Now, we talk about attributes. Since I just stole all these classes, SD classes from assignment 3, and that do not have those attribute fields. So if I want to, as I did yesterday, to associate attributes with a node, I have to add fields to those corresponding classes. If you recall what we did yesterday, S node has a field called val because that's used to record the value of the whole expression. So we add that, highlighted in red. Remember, every expression also has 3 attributes, because for that grammar with 3 attributes, is float, it's going to tell us whether there's a floating point expression or not. In other words, if its float is true, we know that expression contains at least one floating point value. If its float is set to false, that means every number is integer. And the type is deduced to be the type for the expression. So if it has 2 values, float, if it's a floating point expression, otherwise it's set to integer, the var again is used to store the value after that expression has been evaluated. So I just got all this. Now you can write a parser. Of course, I'm not going to say anything here because you can see it's about 30 lines of code. You can write this parser. So if we just basically on the project 2, that's the code, but it's too small for you to see anyway. Now on project number 1, that's the implementation. Remember, that's the constructor for the parser. This should be familiar to you by now. The match is a function for matching tokens, terminals, except the same thing I just grabbed from the parser implementation. This is how we implement parse S according to our parsing procedure. I'm not going to explain this anymore. The parse expression obviously checks whether a given expression is syntactically valid. If so, it's going to build a AST representation for that. And parse factor just does the same thing, except that it handles a factor. It's just just a language construct. That's about it. It only has this less than 100 lines of code. So if this, remember that's the input we have been using for this example. Now if you run the parser on this input, now you're going to get that AST for that expression. I mean, if you have done your third assignment, this should be fairly simple to you. Even you are sort of halfway through, this should make more sense to you. So now we have a parser. So that's the tree for the expression 5/2/2.0. So now I'm going to talk about visitor design pattern and how we're going to use that pattern to implement the second approach. The second approach is rule-based. Okay, essentially we're going to implement 2 passes, as you will see shortly. Okay, here's the general idea behind this pattern. It's very simple. And just suppose when we develop a piece of software dealing with trees, and typically you have 2 different parties. You might have one party responsible for building the trees. This could be the guys developing a parser. Eventually, if you give this guy input, this guy is going to return you a tree. Then you have the other party who did not build the tree, but who would like to traverse the tree and do something on the tree. Okay? In our case, that doing something simply means we are going to evaluate this given expression. Okay? And in assignment 4, by doing something on the tree, we're going to do type checks. We're going to traverse the tree, even if that's built by somebody else, we don't really care. I want to traverse the tree, traverse all the nodes, doing certain things on different nodes. Okay, so how do you reconcile, these sort of different requirements among these 2 groups of people? So one pattern is so-called visitor design pattern. So the tree designer will just leave an interface saying, okay, I have no idea what you're going to do, but once I have finished building the tree, design all my tree stuff, I leave an interface for you. Okay, nothing is implemented, and if you want to do something, then please implement that. Okay, so when you implement that, if you look at the names of these methods, that should be clear to you. For our example, you only have these many types of nodes, altogether 7. Now you need 7 visitor methods. The idea is that whenever you want to visit a particular type of tree node, you want to call the corresponding visit method because that guy knows how to process that node type. That's it. Okay, so now you can see in assignment 4, you can implement a type checker. Essentially, you can implement one visitor.
I have no idea.
She's been away for a while, right?
Yeah, the honeymoon was supposed to be like a month.
Month? Oh, okay, that's a long time.
If it was like middle of March, then she'll come back middle of April.
Was it middle of March? Was it only
The wedding?
early
Oh
March?
no,
right?
the wedding was like 1st of March, yeah.
Oh, but she left like middle of March.
No, she left like, still early March. So
Oh.
she'll come back early April, I guess.
Oh, that's actually quite long.
Yeah. Oh, it's not too bad.
Month, yeah. Month is like pretty decent holiday.
Yeah.
Like 4 weeks, right?
Yeah, like short time in Philippines and the rest in Japan.
Yeah, that's so like 3 weeks in Japan or something.
Yeah, that's a long time in Japan.
That's good. 3 weeks.
It's not as long as your brother.
Like when I go to Japan, I usually go 3 weeks.
3 weeks? Oh, I went 2 weeks and I thought that was like enough.
Really? Nah, 3 weeks is okay. I think 2 weeks is slightly too short. Like
okay.
when you say 2 weeks,
like
how long do you mean 2 weeks? You mean 16?
Yeah, days.
16 is alright.
Oh, okay.
But
I guess there was some other things I wanted to do, but we crammed a lot.
yeah.
So if we had more rest days, then 3 weeks would be
Nah, I always cram when I go.
You cram as well? Oh, okay. Yeah, that's fair.
Yeah.
What was the sermon about?
It was on Psalm. One of the Psalms.
Yeah.
Talking about how we should respond to our salvation and stuff. But to be honest, speaking of it, I couldn't really understand.
Or was it not?
It wasn't. It was like Ronald from Cantonese.
Oh, yeah.
So-
was he wearing a suit again? Or was it
A bit
different-
formal.
Hmm?
I don't think he was wearing a suit, but a bit formal.
Oh, yeah.
But yeah, I don't know. Like I can't tell. His accent's a bit funny, for one.
Is it not just like a regular Cantonese accent?
Yeah, it is. But I think it's combined with like he was like like the sermon he wrote more like a essay rather than like a sermon.
Oh.
So like
okay.
combine those and then it's a bit hard.
Yeah, that's tough.
But what's about? Let me see where I write. About yeah, I mean thinking about salvation and like who it's for, like for humble.
Do you know which psalm it was?
160.
Oh, I don't even know if I know.
Yeah. Like this is like a testimony, and like this is how, yeah, it's like, yeah, like what looking at what God has done, and then how to remember that as well.
Oh, okay.
Something like that.
Interesting.
Yeah.
Did you guys have dinner as well after?
Yeah. Let's go to the Viet place.
The Viet place? Oh, you didn't bring food back to church?
Nah, not this week. I'm not sure about that.
Fair enough.
Yeah, I don't know.
Should be okay then. Maybe next week they'll bring back food, then I can save money.
Oh yeah. I mean, I prefer bringing it back actually. It's nicer. Like
It's nice.
we get the space to all to ourselves.
Oh, the Viet place is pretty small.
Yeah, right. As well.
That's true. Yeah.
And like, yeah, I think it feels a bit nicer to have in church.
Yeah, I think. Oh, I like it because it saves money.
Yeah, you say money. You bring food. Just bring out your food.
Yeah, that's smart.
Every type of tree node. Then that guy is responsible to do the type checks on the node. In assignment 5, you can implement the same interface, except that visit method this time is going to do code generation. Okay. Whenever it visits the tree, for example, for the type checker, you look at the binary expression, you can say, oh, okay, this expression work well typed. But if you're the guy developing assignment 5 doing code generation, you can say, let me translate this expression into a bunch of instructions so that can be equivalent execute on my JVM or x86. Okay, so that's the idea. Now, you see the parameters. I mentioned that every method has a second parameter, O, so that allows some inherited attributes to be passed into that method. Remember, inherited attributes are passed from outside into this particular rule because they're inherited. You need to pass that from the parent node. You can pass that from your sibling nodes to you, but anyway, they need to be passed to you. Now, if you want to return certain things to your parent node, that's a synthesized attribute. And you can use the return statement in each of these methods to return that to the parent node. That's how two types of information sort of flow on the tree. Now, so I'm going to just say a little bit here. So now we want to implement our attribute grammar, example 1, and we are going to have a visitor. So this visitor's responsibility is just to evaluate the attribute grammar in example 1. Now we need to implement all the visit methods. Okay, as you can see here at the bottom of the slides, we have an XY visitor. You can call it whatever you like. It has to be implementation of the visitor interface. And you have the responsibility to implement all those methods. Okay? Ignore the top part of the slide for now. Just look at the bottom slide. So you need to implement the interface. Then you need to implement each of its interface methods. Now, we are looking at this visitor binary expression. Because it's called a visitor binary expression, obviously, the guy has two child nodes. So left child and right child. Whenever you visit this guy, you want to visit his children, right? So the visit design pattern just allows you to exploit, the dynamic, the polymorphism provided in OO languages to do this sort of a easy way. Okay, let's just look at an example here. Even though you don't fully get this, it doesn't matter. You're going to practice this anyway. You understand everything in a few weeks. The idea is here is just okay. Okay, here's the idea. So remember, the visitor's interface has many methods. One of them is called visitor binary. Just make this a little bit bigger. So one of them is a visitor binary. When you implement this, you want to do something on that binary expression node you are visiting. Whatever you do depends on the nature of the task you're performing. Obviously, you do something on that, you have to visit its two child nodes, because otherwise you're not going to visit all parts of the tree. Now the question is, how do you do that? Okay, so if you make use of polymorphism, it's very easy. We just say, if AST in this slide is the pointer pointing to this particular expression node, then you have another 2 pointers pointing to its 2 children. So one is st.e1, one is st.e2. Let me just draw it here for you to make it easier. I'm still going to use this. Just do it slowly. So, suppose we have a pointer pointing to this particular binary expression. Okay? According to our, let's just look at the ST here. Now, if you look at the definition for binary expression node, it has 3 pointers. E1 is a pointer pointing to the left expression. That's like a left child expression. The E2 is the pointer pointing to the right operand, which is expression. O is just the operator. Just forget that it's plus, minus, whatever. Okay. So essentially here, there are 2 pointers pointing to its 2 sub-expressions, which are its 2 operands. That's it, right? So now, when we are visiting a binary expression, we have a pointer SD pointing to this particular node. At the same time, this guy, I cannot talk. So the left child can be found by following this pointer, the right one. So this is ST E2. So basically you have ST which points to the parent, ST.E1 pointing to the left child, ST.E2 pointing to the right child. Okay. So do remember, if this is the pointer pointing by this guy. I mean, as you can see, we have a pointer here pointing to 3 different binary expressions. We have no idea what sort of types of expression we expect to see, for the 2 children. For example, if this is the case, the left operand is a float point expression. If in this case, this se.e1 is integer expression. In this case, this happens to be an integer expression. So what that means is you really don't know when you are going to visit a child node, whether it's a binary, integer, whatever. So how do you do that? Well, you have 2 ways of doing that. As you can see here, in the purple color here, that's one way. You can just use sequence of if-else statements just to check, go through all the possibilities. You want to visit the left child, you want to say, hey, what are you? Are you a float expression node? If you are, I have to call visit float expression. If you are integer expression, let me just call visit integer expression. You got to enumerate all the possibilities. That's one way of doing that. By doing that, you sort of you're not leveraging the polymorphism provided by Java. Instead of doing this, we can simply just call visit on AST.E1 because visit is a polymorphic call. Okay? So depending on the type of the object, or in other words, depending on the type of the expression node, different visit methods will be called. Okay? Let's come back to this example. So if we happen in this sort of scenario, then AS.E1 will be pointing to a float expression. So if that's the case, since we understand well polymorphism, when you call visit on this guy, then this method is called because sc.e1 is a float expression. Based on that dynamic type, this particular visit method is called. Once this guy is called, this guy says, look, you're calling this visit method. Of course, I know what I am. I'm a float expression. Okay. Now this guy immediately calls visit float expression on V. V is the visitor. So basically, you do it in such a roundabout way to decide whether it's a float expression or not. This way, the code is cleaner. There's other advantages I can talk about. Okay. Now, if ASD happens to be pointing to this guy, in this case, ASD.E1 will be pointing to an integer expression node. If that's the case, because the dynamic type of this expression, this pointer, E1, is an integer expression, now this guy is called. And what this guy does is very simple. Because I'm an integer expression, let me just call your visit integer expression node. And similarly, in the third configuration here, because we have this is integer expression. That's not a, let me just get rid of this. Okay. So in the third configuration, SD is pointing to a binary expression. Now if you look at the E1 node, it's pointing to another binary expression. If that's the case, now this guy is called. Whenever this guy is called, it just says just call your visit binary expression. As you can see here, we look at this implementation. So what this one line does is exactly equivalent to what we did in those lines highlighted in purple color, because we just simply take advantage of polymorphism to do that. Okay. So apart from, obviously we do not like the code highlighted in purple because it's longer. What are the other advantages of using the, leveraging the polymorphism when we traverse the tree? I mean, obviously it's shorter. It's one line. Here's like 6. What are the other benefits? Yeah, obviously the readability. I mean, it certainly improves the readability. Yeah, extensibility. Yeah, because for example, suppose one day you're going to add another type of binary expression. You might add a double expression though, because you're going to allow double values. Now, if you take the second approach highlighted in purple color, you need to go through your code, look at all these blocks of if statements, and making sure you add an extra branch. Otherwise, your code is going to crash. It's not going to work. However, if you do it according to the first approach, it will be very easy. All you have to do, as a tree designing guy, is what that guy is going to do. Because a new type of node is added, so the tree designing people will just add a visit double expression into the visitor interface. Now, as somebody else who likes to traverse the tree, and you just need to implement that method. You don't have to do anything, okay? Because that method will be automatically called as long as you have a double expression somewhere. Okay, that's another advantage. Okay, do we have any questions? Don't worry about it. I mean, you have to use this as the last two assignments. Now the logic, we understand this, and the logic will become, let me just delete all this. We're going to look at this later. So basically, if we're visiting a binary expression, it depends on the nature of the task you do here. You can visit it to children, just that way, you can do something on the node. Okay. So if you're interested, you can look a little bit more on the internet. Now, there's a tree, and you just need to implement. The first approach is it will be very the tree designing guy is what that guy is going to do. What type of node is added? Because a new type of node is added to the tree. Somebody else question. How do you do here? This one is called a rule-based approach. So if you're interested, you can look a little bit more on the internet. Now, we take a look at the second approach of evaluating the attribute grammar in example one. Okay, this one is called rule-based, in the sense that as we are, let's say, compiler developers, we are familiar with attribute grammars. We look at the semantic rules given, possibly assisted by some tools. Then we realize, hey, there are a bunch of rules. There are 3 attributes, but we can possibly evaluate all the rules using 2 passes. Okay, in the first pass, when we traverse the tree, we are able to compute isFloat attribute, as we did yesterday. Now in the second pass, we can evaluate the remaining 2 attributes, type and value. Okay? To do that, we're going to create 2 visitors. Okay? The first one is called a float visitor, because we're going to evaluate isFloat attribute. And then we create a second visitor that's going to evaluate type and value. Once they've done that, we should be able to see the val available at the root of the tree. Okay, so let me just okay, for those who are here, it will be easier for you to just look at the semantic rules in page 298 on the second projector. Okay, now let's see how we can implement this. Okay, so we look at the first visitor implementation. Its responsibility is just to evaluate all the rules related to isFloat. Now, if you watch like the recordings, you need to look at page 299. So if you look at the page 299, there are only 3 rules. Now we're going to evaluate these rules by using a visitor. How do we do that? We just implement the get interface. Remember, that has 7 visitor methods. Only 3 rules. Remember, this is synthesized. We only evaluate these rules during the post-order traversal. Now, let's look at our implementations. So visit S. Okay, let's just come back to this. Okay, remember this is the interface. There are 7 interface methods that we need to implement all of them. So visit S. Now if you look at the rules in page 299, there's no rules. We don't have to do anything. All we have to do is, whenever this guy is called, we start from the root. What do? Visit this guy's sole child node. There's only one child node. Just visit that. Okay? So now if we look at this tree, that means we're going to descend to a binary expression node. Okay? So this guy is called. So once this guy is called, this guy says, I'm a visitor. I'm responsible only evaluating a synthesized attribute. So I only need to do that after I have visited these two children. So then you visit the first child, you visit the second child, then copy that rule at the very end. That's what you do. Okay? Because you have already deduced this attribute from each of the two children. Those are available. Then you are able to apply the rule to compute each float attribute as the parent node during the post-order traversal. So again, if you watch like a recording, you can just look at the page 299. Okay. So visit integer expression. Obviously, look at the rule in page 299. Just implement that and return. There's nothing else you have to do because there is a leaf node. If you look at the tree here, there's nothing you have to do once we are there. You have to remember this is done recursively, okay? Even originally we are here, then recursively, eventually we are here. Now, if we are visiting a floating point expression, and just implement that rule, then we're done, okay? So effectively, if somebody has designed a tree for you, there's a parser which has constructed the tree for you, and you want to traverse the tree, do something useful according to your task given, you implement the visitor interface. Whatever you do there is up to you, nobody else really cares. In our particular case, we are responsible to evaluate the first synthesized attribute only during the post-order traversal. So that's the first visitor. And that's it. And here there's nothing to do. We simply return now because we don't have to do anything. Because what this means is whenever we hit 5.2, 2.0, we don't have to do anything. There's nothing to do. So that's it for the first visitor. Now we're going to see the implementation for the second visitor, in which we're going to evaluate all the rules used for computing the last two attributes. And this will be the rules given in 2 in 300 and also 301. These are the rules. Okay. Now, if you look at the rules in page 300 in yesterday's lecture, and that type is inherited attribute. You need to evaluate all these rules during the pre-order traversal before you visit a node children. Okay? Pre-order traversal. Now, the rules in slide 301 in yesterday's lecture, these are responsible for evaluating val, which is synthesized. You only apply these rules during your post-order traversal. Okay? Now, with that understanding, it's just a matter of copy these rules into the code. Okay? Now, we take a look at the second one. Second visitor.
Corrupt file history. Huh?
See here, we are visiting, we start from the start node. Okay, as you can see, this time we have to do something. Why? Because now, take a look at the rules in page 300. So we essentially just copy those rules. Okay? If this guy is a float, set this guy to float, otherwise set to integer. Now, you
visit S. This expression type is float identified. ASTE. Also, you have to visit it before you can find the value, but we know that the value will be.
Visit the only child for the S node. So before you return to the caller, you need to evaluate the var attribute, because that's a synthesized. You apply this rule. Okay? So essentially you have two sets of rules. The first set must be done before you visit this child, and the second rule done after you have finished visiting this. That's about it. Now visit the binary expression. Okay, see, you see these two rules? These two rules are literally copied from those two rules in page 300 because these are the rules for evaluating type. The type is inherited attribute. Okay? Before you visit these guys' two children, evaluate those rules. Now, once you have visited these two child nodes, then you do all this stuff. And what are these? Just these rules in page 30. You just copy that. Okay? All they're saying is, now I've finished visiting the two children. I would like to see whether I can evaluate this expression, if this is all available. Of course it is, because we are able to evaluate both in one pass. Now you know the type, you do your evaluation, and according to those rules. As you can see, we essentially just, kind of paste the rules. Of course, we have to use the Java syntax to implement this. And visit integer expression. For page 300, we don't have any rules to apply. Right? So then, obviously, there's nothing we have to do before we do the visit. Now, this rule, let's copy it from here, because this guy is synthesized. Similarly, float. Okay, if you look at the float, there's one rule, because this rule in page 301, that's used for evaluating val during the post-auto traversal. Then you just do it. That's it. There's nothing else. Now we'll have empty implementations. Now if we just take a look at, so basically this is the main program. I again just copied our main program here. We have a scanner parser that builds the tree, and then we create a parser that creates the tree, it draws tree on the screen, create the first visitor. We start traversing the tree from the root of the tree. Then we create the second visitor. We traverse the tree from the root. And finally, we print the value available with the root. Okay? Now we will run this. So you see the tree created by the parser and showing on the screen by using the tree drawer. At the same time, if you look at the output from running this program, you see the type. You also see the value. Okay? So this is so-called rule-based approach. And any questions? All good? Okay. The idea is just to have an intuitive understanding about attribute grammars, attributes, semantic rule, the evaluation, two different approaches, tree traversing, very simple. You just traverse the tree like crazy, from top to the bottom. Aggressively evaluate every rule that can be evaluated. By respecting the data dependencies. That's it. For the second approach, we analyze the rules. We know how many passes we are going to traverse the tree. We know which attributes should be evaluated in a given pass. We fix the rules used. That's why it's called rule-based. In the first visitor here, float visitor, we only evaluate the rules for computing each float. By using the second visitor, we only compute type and val, the other two attributes. And once again, you evaluate rules before you visit a particular node. You evaluate certain rules before you visit this guy's children if those rules are responsible for computing inherited attributes. Because you inherit something from his parents, you can immediately do that. But if you have rules computing synthesized attributes, you only apply them after you have visited all the children, because you have to synthesize stuff from all the children. You cannot apply those rules before any of those. Any of these guys' child nodes has not been processed, because otherwise those values will be undefined. So this is the code. If you're interested, you can take a look. So that pretty much actually tells us how to implement a parser better. It also prepares us for the last two assignments. From next week, we're going to talk about semantic analysis, because your parser will be due next week, and the specification for assignment 4 will be made available just at the end of last week, and then there's a break there. So by the time we hit the flexibility week, we should have finished the first 3 assignments. It'll be just 2 more to go. So yeah, that's the code. If you're interested, you can take a look for these 2 visitors. Okay, I said I have 3 examples. I'm not going to spend too much time on the last 2, okay? Because somebody asked me a question that's related to this. Okay, remember, if we go back to the first. I mean, if you watch like recordings, you can look at page 287. I mentioned 2 types of attributed grammars. So here we can take a look at these 2 error attributed grammars. So they're always nice special cases. Now here we have 2 special cases we like to have. So one is called error attributed grammars. So what that means is I can draw somewhere.
Or uses what to know.
So if here you have a node called whatever x0, they have a few child nodes. Say here's xi and just a lot of other nodes. So let's say we want to compute an attribute A, whatever that is, it doesn't matter, at this ith child node. Okay, so what is the error attributed grammar? I mean, if you look at the definition, it's a lot of sentences. All we are saying is attributed grammar is error attributed. Okay, if you only use the attributes from here and from all the siblings sitting to the left, that's L attribute. L means left. Because think about it, if that's the case, that would be very nice to have. Because when we do a pre and a post order traversal, by the time we want to compute something at the ith node, anything we want to know has already been available. Okay, because it's on the left. Okay, provided we visit all the children from left to right. Okay, so if that's the case, if you look at this slide, it says this is the definition, because the information flows from left to right. If you have an error attributed grammar, you can always evaluate all the rules in just one pass. That's top-down parser. So that's the algorithm. It says start from the root of the tree for each child nodes visited from left to right, evaluate inherited attributes. Here we talk about inherited attributes. Essentially, look, now you have a synthesis attribute, then you do it during the post order traversal. Then everything, those will be evaluated in just one pass. Okay? That's because you don't have, when you work on the ith node, you only use information from left, not from the right. Okay? So here's the example. This example is relevant to your current assignment, but I'm sure some people have already figured out a way, because I've seen quite a few submissions. This is part of the grammar from VC. As you can see now, we should understand this very easily. So we have a few productions. We use these productions to define a declaration statement. Every declaration statement starts with a type. We have integer float. And that declaration has a number of variables, identifiers. That's it. You must have at least one identifier. Okay? So, let's say we want to give an attribute grammar to build the AST. Remember, in our third assignment, if you have a variable declaration that contains 10 variables, you need to build 10 variable nodes. Let me just show you. I was marking around something.
Okay.
I've been changing things a few days. I don't know, I might have changed something. Just forget about it. I want to show you the tree, but the tree is on the screen anyway. So basically, because I've been modifying my implementations these few days, I want to make it a bit different next year. So let's say if that's the declaration given, if you are implementing your parser, you need to link all these three different declarations that way. Okay. However, that's not exactly what I wanted you to do in assignment 3. Okay, because as you can see, this is the parse tree. This is not the syntax tree. This is the parse tree, which you can build by using the production. This is not ASD. Now, this is the ASD we want you to create. So essentially, you need to let me just see. Must have changed all this stuff. Yeah, it doesn't work. Okay, okay. So eventually, if you look at our requirement, you see. Should be here as an example. See, here we have a declaration in which we have, so we have a declaration statement in which 3 variables have been declared.
Why is he lag?
Let me just copy it. Correct. As you can see here, we have three variables being declared on the same line, even though the type only appears once. We ask you to build 3 different declaration nodes in which you can see the int in 3 different places. And that's the idea. Now I'll come back to the example. Suppose that's what we want to do. And if you watch lecture recordings, you need to look at this example T37 in the specification for assignment 3. Okay, so suppose we want to build a tree like that. How do we do this? The idea is very simple. You can do that by writing an attribute grammar. This is what we are doing. Let's try to understand what this means. So the idea is very simple. We have an attribute called type. So every time we see int, we set the type attribute for t as int. If it's a float, we set the type attribute as a float. Very simple. Okay. So the attribute type remembers whether the integer type or float type. Okay. Now look at this production. So the type information is available at t, but we need to pass that information from t to L. Okay. So that because we have a lot of identifiers, so essentially we need to pass that information from t all the way to different identifiers. So if you look at this tree, what that means is we know the type information here, but we need to pass this information all the way to all these different L nodes so that we can create
This was
a
kind of tricky
declaration
to do
node
myself.
with that type. Otherwise,
Does
how
it
do
give
you
us
know?
a solution?
Because let's say you want to
Then
build
I
a
should
node.
exhaust this like.
Okay? A node, according to this example on the right, must have a type. So you need to pass this type information all the way here. How do you do that? If you use attribute grammar, that's the specification. So you deduce the type at t, you pass that information from t to the first L, then you do that recursively from the L to L1. L1 is the child node of L. So eventually, if you look at this slice, that's how the information is passed. We get the information here, then we assign this attribute to L, then we pass this attribute all the way to this L, to this L, and to this L, until everybody knows we start with int, not a float. So once we know the type, we are able to build an integer declaration node, and then combine that with this one, and eventually we get a linked list. So that's essentially what you see here. So you see the first type information, you pass that so you're roundabout way, and then you build the nodes, then you link them together. Okay. So this is pretty much. If we allow you to use a global variable, it's very easy. You initialize a global variable with the type information, then you just access that because that's not allowed. Guys, I ain't got to do it in such a roundabout way by passing information around. Okay. As attributed grammars are even simpler, that means it is a attributed grammar in which you only have a synthesized attribute. Everything just moves bottom up. Okay, everything can be evaluated in one pass. Okay, that's it. You saw this example. 2 weeks, 2 weeks ago. So that's the example. So on the left, we have this classical expression grammar. On the right, we have a few rules that are responsible for converting expressions from the infix notation to the postfix notation. And that's the formal specification. There's only one attribute, T, that always represents the postfix representation of that infix expression. I did this last 2 weeks ago. Here's the example I drew that. So basically, if we are given, in this case, you can see on the left-hand side, the expression given is 1 plus 2 times 3. Okay. So if that's the expression given, you can build the path tree on the right. Now you can evaluate all the rules bottom up. And eventually you get 1, 2, 3 times plus. So that is the synthesized attribute. I explained this 2 weeks ago very quickly just to provide motivation for this week's lecture. Now you see, you should, hopefully, you think this is easier to understand. So you have the rules, you have one attribute, since that is a synthesized, you would like to compute that attribute for every node. If every node represents the expression, that attribute gives its corresponding postfix notation. You simply just apply rules. I did that before, I'm not going to repeat that. Just briefly here on the slide, you can see clearly one's postfix notation is 1, two's postfix expression is 2, and eventually on the right hand side, you have 2 times 3. And whenever you're in that situation, as I did last time, you can apply this rule. When you apply this rule, you simply just concatenate postfix expression of the left child and the postfix representation for the right child, and then you put the operator at the very end. Then you get 2, 3 times. Here, you have a plus, then you apply this rule. Okay? This means string concatenation. It shows how you can concatenate these 3 different results together. You simply concatenate 1 with 2, 3 times, then eventually plus. That's what you get. So this is a synthesized attribute. Okay, 2 special classes of attribute grammars are attributed, in which every inherited attribute can only be computed by using attributes in the left siblings and from the parent, but not from the right siblings. Synthesized attributes are even simpler because we even do not allow inherited attributes. This looks like naive. In reality, this is used often because when it comes to implementing last 2 assignments, all the expressions will be handled this way. How do you type check expression? Type check bottom up. You deduce the types for small expressions and use this type information to deduce the type for the large expression. How do you translate an expression? You translate the smaller ones then you use the translated result to translate large ones. Essentially, you type check or translate any large expression inside out. Okay, so you deal with smaller ones, you make use of intermediate results. Eventually, you finish what you're supposed to do for the expression given. Okay, so what should we know about attributed grammars? As I said, in some European universities, because they tend to have a more emphasis on formal things, they might have a course on this. This, I think, is important because sort of interleaves with a lot of things we do, even though I never ask you to write attributed grammar first before you can write your parser. Okay, you write attributed grammar to formalize the type checking process before you can write down your type check. We didn't do that. However, implicitly, everybody's doing that anyway. Okay, so I'm going to talk about the requirement because in every year's examination we always have questions. So basically, we need to know what attributed grammars are. If we are given simple tasks as you have seen so far, like conversion of infix to postfix expressions, very simple toy grammar for evaluating mixed mode expressions, then you should be able to write down attributed grammar for them. And if you are given attributed grammar, you should be able to evaluate that. Okay? By evaluating that attributed grammar, what we mean is if we are giving you a parse tree like this, you should be able to annotate or decorate. It's called decoration, whatever. Essentially, you should be able to compute the attributes. Eventually, you're left with a tree in which all the attributes have been computed. And we said the original tree has been annotated or decorated, whatever, it doesn't matter. Yeah. So you should be able to do that. Yeah. So you should develop a basic understanding about attributed grammars, be able to write down small attributed grammars, be able to evaluate those attributed grammars, and you should be able to, show your evaluation by decorating the tree, by just drawing the attributes on all the nodes for a given tree. That's about it for today's lecture. I just want to do a little bit slowly before we move now. If you are interested, now you can take a look at these different packages we use for marking assignment 3. They are all implemented using visitor design pattern. See, if you use our, provided tree drawing package, you should be able to see a ST showing on the screen for the tree you created by your parser. As you can see, that's a visitor. So that's a visitor that implements the visitor interface. And if you go to you can see, that's the visit interface. So basically, you have a visit method for every distinct type of tree node, right? So we have a statement list, we have a visit method for that. If statement, you have to have a dedicated visitor method for that, and you have as many visitor methods for the number of different types of nodes we have. So now, if we want to draw the tree on the screen, we just implement the interface, and as you can see, this is how everything is implemented. It says, we see an if statement, we're going to draw that on the screen. Now how do we draw that? That's basically how it's implemented. If it's an empty expression, though, remember if statement, the else part is optional. Okay. So if that's optional, how we draw it, otherwise it comes with the else part. Then we just call this auxiliary method, layout tertiary. What that does is you take the if statement, that's the name for the node. This guy has 3 phrases, remember? The conditional expression, the then statement, and the else. Essentially takes 3 pointers. You just call this layout ternary method. Let's just I think it's somewhere here. Yeah, that's sort of implementation using Java Swing. So essentially, you have a name for the node, it has 3 children. You just figure out how to draw these on the screen. Everything is sort of done recursively. What this says is, you asked me to draw each statement. Now I want to recursively draw these, the 3 children for these guys. Because you can see, just doing this recursively. That's it. Okay. So essentially, so each of these is a visitor that's being implemented. It doesn't hurt if you take a look at that, especially before you start working on a loss assignment. So next week, we're going to talk about static semantics. We're going to have 2 lectures. In the first lecture, we'll just give you a review about the scope rules, the type rules. In the second lecture, we're going to look at how to implement a type checker. So essentially for assignment 4, half has been done for you. You will know what that means next week. Before we go, so yesterday I did not show you, I normally show you a sort of a representative solution from the class. I didn't do it because for the second assignment is straightforward. I just grabbed one implementation from one view. As you can see, it has just about 400 lines of code. As I said, it's not a competition about who can have the least number of lines. It's really not much to say here. So you do a left factory elimination because function and variable declaration share 2 tokens as the common prefix. You need to sort of deal with the first 2. Then you decide whether you're going to handle that as a function declaration or variable declaration. So everything else, as you can see, is sort of straightforward, just according to the Python template. And yeah, and this solution uses some a few help methods. I mean, you're free to do that. So out of like 180 solutions, I think about a quarter, they have like just under 500 lines of code. And some solutions a bit too long. And if your solution is 500, 600, fine, but not like 900. And sometimes 1,000 lines of code is a bit too much. You really don't need this many lines of code to write a parser. So pretty much it's like 400 lines of code should be. Okay. That's all I want to say today. Any questions? All good? All right. I'll see you next week.
536. What? This guy's doing 1-hour lectures. Thank you, I guess.
parser. We've done 2 lectures about attribute grammars to understand intuitively what they are. We're going to make use of them.
Like Helping people
normally in developing the last two components. In assignment 4, we will focus on so-called static semantics. Really just type checking. So when you talk about static semantics, when you talk about type checking, you normally mean two things. First thing is if you make use of, it's called identification. Okay, one is identification, the other one is type checking. Identification in assignment 4 has been done for you. So what that does is just to relate every variable used with its declaration. Because EC, like Java and C and C++, EC is only type, statically typed. It's different from Python and JavaScript, all that. So if you want to use a variable, you have to declare it. Otherwise you can't. So that means every variable, if you want to use it, there must be a corresponding declaration. So the process of identification is just to relate these two. The other part of the story is type checking. So you make use of type rules. So you make use of scope rules to do identification, and you make use of type rules to do type checking. So it's pretty much what you will do. So 2 lectures this week before the break. So today I'm going to talk about identification. This is something that has been done for you in the starter code. And you are going to complete that by doing type checks. Then you make use of type rules to do type checking. So it's pretty much what you would do. So 2 lectures this week before the break. So today I'm going to talk about identification. This is something that has been done for you in the starter code. And you are going to complete that by doing type checks. So yeah, assignment 4 you'll be given just 2 test cases. The first test case, both test cases are syntactically valid. That means your parser is going to pass both successfully. However, they all contain a bunch of semantic errors. You might have seen something already. For example, 1 plus 2 equal r, that's syntactically correct, but semantically meaningless. Anything here like, in our language, we cannot return a floating point value from a function whose return type is int. It's just not allowed in our language, just like Java. All these are specified in VC stack. You might want to take a look. So once you have finished your assignment 4, if you want that through, you're going to see, just a bunch of error messages. Almost like every line has an error message. Second test case is mostly related to arrays, because we have a one-dimensional arrays, and almost everything here is semantically problematic. For example, array of 2 elements has been declared to hold integers. However, we put too many, that's one. But the other thing is, put a string inside, that's not a real type. Here, for example, I is a variable, but we have used it as an array. X is array, but we have used it as a variable. And so on, so forth. All these need to be flagged by your, so when you run through your type checker, you're going to see a lot of error messages. So as I said, we're going to look at the identification, how to use the scope rules, just to link every use of a variable to its corresponding declaration. So in the most general case, of course, if you talk about real language, production quality language with a lot of other facilities, you've got to do more checks. But the fundamental idea behind static analysis is the same. So before I go through all these, I'm going to run through a few examples to see whether you have some issues with your understanding of these concepts. So we look at the first example. This is a C. So we probably know whether this compiles or not. Right? This is C. Do you think this compiles under C? Yes or no? So this one, of course, there is some issue because here you want to call C, but C has not been declared early. So here's sort of the equivalent version of that program in Java. Do you think this Java program will compile? As you can see, it's like we have a mutually recursive calls. Inside X we call Y, inside Y we call X. But do you think this will compile in Java? But it doesn't compile for C. So this one compiles fine. So what about this one? So we have a declaration like that. Is any issue according to the scope rules? Would you see some error messages when you use the C compiler to compile this? Oh, okay, let's say we add that. Let's say we just add this one. For that assignment, is any issue with that? So that compiles for C. What about this equivalent Java program? Do you think this will compile? Very quiet. Yes or no? Yes. Answer is yes or no.
Integer, not int.
So this one doesn't compile, says variable I might have been initialized. It's not been initialized. So that means if we do some initialization here, and it will compile. Does this compile? What about this one? So we have the same variable here and also there. Does this compile under for Java? Yes or no? So this doesn't compile. So what about this program? Integer is a class defined in the Java package. So if you try to compile this, will this compile? I mean, you see this already. So with import, it doesn't compile. So comment this out. And it compiles. this one then. So we have variable x that's declared twice. Once as a variable, once as a function. Is C compiler happy with this? No. What about Java? So X has been declared as a method and also as a, a field. So Java compiler likes it. So hopefully you pretty much understand all of these issues. If you don't, that's not a big deal. The point I want to make is that for a computer science student, it would be a good idea to understand all this and to understand also the reasons why some of these programs compile and some don't. The principle behind all this is quite simple. It's all related to scope area. So we do that by first talking about blocks. Blocks are component statements. I'm not going to read all this stuff. So basically, we are all familiar with curly braces. Every computer science student, whether you like it or not, and you deal with braces every day. So a pair of braces is called block or component statement. Okay, so what is the scope? The scope of a declaration is really just part of the code over which that declaration takes effect. So you have a declaration, you want that to be useful. Now, which part of the code does that declaration make sense? That's the scope rule. We say a declaration is in scope at a particular point in your program if and only if the scope of that declaration includes that point. So that point is in that scope. So what are the scope rules? It's just a bunch of rules by which you can identify which variable uses are related to which declarations. For all those test cases I've gone through, you only need to know the scope rules in Java and C in order to understand whether each of them compiles or not. So basically that's the scope rules. So we're going to go through our scope rules. Most of these I would consider the revision. It's nothing new today. This is for a 30-year course. Everybody should understand all this. Okay. Already, I said not understand this today. Okay. We have a few scope rules. Firstly, we talk about scope of a function. So whenever you define a function, you want that function to be called. So then we say the scope of that function starts immediately from where it is declared and goes all the way to the end of a file. Because in our VC language, we only have one file. Okay, we do not allow multiple files. So that means you have a function declaration, that function becomes callable starting from that point all the way until end of the code file. Then scope of a variable in a block. A block is a component statement. It starts from the point at which is declared and becomes valid all the way until the end of the block. This one is related to one of the examples I just showed you. So if you have two parameter declarations, where are their scope? By definition, the scope of any formal parameter is the same as the local variables containing that function. So effectively, whenever you see a function declaration like that, you can treat this parameter declaration effectively as a local declaration. also have some built-in functions. By definition, every built-in function is available for the entire program. That means anywhere in the program you can call it. Entire program. That means anywhere in the program you can call it. Number 5 is quite simple. It says no identifier can be declared twice or more than once in the same block. Okay, and 6 and 7 are not normally going to read them. This is sort of rules available in most high-level programming languages. I'm going to see some examples. You should know what that means. Okay. So look at the input that means. So look at the implication of rule number one. So if you have this sort of two function declaration, according to our scope rule, this program is going to generate a semantic error because the moment you call G is not in scope. Because G is defined, declared only later. That's why in C, in order to make this program compare, you have to use external declaration, just to declare the function earlier so that compiler knows there is a forthcoming declaration somewhere. So that will be part of the bonus assignment, because I mentioned there is a bonus assignment. So one of the things you will do in the bonus assignment is just to add this sort of extra declaration to make the program like this. Semantically correct. So this example is going, just to help you understand, the last two rules I did not explain because it's already something everybody should know by now. Okay, so I've used all these colored bars just to highlight the scopes for all those identifiers. So here we have integer k, that's in both fonts. As you can see, that k as a scope really occupies the whole file. Start from where it is declared goes all the way down. Now look at this function for FOO. It starts from where it is declared. It goes all the way to the end of the file. This variable in red color starts from here, goes all the way here. However, there is another declaration of the same variable in a inner block or inner scope. This is what that slide was trying to say. Okay, whenever this happens, it creates so-called scope hole. So that means this red eye is only available in this segment, and also the second red segment here. Here in the hole, whenever you mention I, you're only going to access this I in pink. So then we say this variable in pink, the scope starts from here, goes all the way. So that means that's like the so-called scope hole. That's basically what these two paragraphs trying to say. You can read this yourself. And there is a variable k that's declared here. The scope goes all the way to the bottom. And we also have this so-called built-in function for integer error in. By definition, it's available in the entire file. Okay, so this program is relatively simple. Now, this program, okay, I just want to. So I've written an equivalent C program because put integer error in is our built-in function. It's not available in C. I have just defined them because above here it doesn't matter. But look what we have done. We have declared this guy as a variable, we use that as an integer here, then we for this guy, then later on you for the other function. Do you think this C program compiles? Yes or no? No? Anybody would say yes? So this one actually compiles. It compiles, as you will understand very shortly. If you look at this slide, we have foo, which is initially declared a function, but immediately inside here, in the parameter list, is redeclared to be a parameter. Okay, that's perfectly legal. Then, in the second line, if you refer to foo, you're actually referring to this red guy instead of the yellow one, the parameter instead of the function. Okay, you can't refer to the function, but it's hidden. So the foo is declared, but immediately hidden. So the parameter scope starts from here, goes all the way to the end of this function. Then we have this guy, that's put integer. Okay, it's redeclared as a variable, so it starts from here, goes all the way. That's why you can use this one here. And it's also built-in put integer here. By definition, this guy is available from the start of the code and goes all the way. However, there's a redeclaration. So then we say this declaration hides the original built-in function. There's no way you can access that built-in function anymore inside this scope. However, every time you refer to put integer error in, you actually refer to this variable declaration. Okay? So this is perfect legal in C and also perfect legal in VC. At this stage, you might think this is strange. Of course, I'm not trying to encourage you to write code like this, but it does compile. To understand why this compile, it's very easy. We just introduce this simple concept of scope level. So that means in VC, all the global declarations reside at the scope level 1. So that means we start with the scope level 1. That means all the global function declarations, all the global variable declarations reside in the outermost scope. That's the largest scope possible. Okay, that scope by definition is given level 1. So every time you go from the largest scope to a smaller scope, you increment this variable, this level by 1. Okay, that's just the definition. So in VC, all the function global variables at level 1, and rule number 2 says every time you create a nested scope, you sort of increment the level by 1, and all the built-in functions by definition appear at level 1. These are our rules, 3 rules. Okay, just once again, all function global variable declarations at level 1, and we have this nested scopes, and if you have a maybe I can draw something. So if you are talking about so let's say this is at level 3. Now you suddenly have another linear scope that will be level 4. That's basically what we said. Okay? So a pair of curly braces is a scope. Every time you create a nested pair, that's another scope. Okay? So you simply increment the level by 1. So given this concept of scope levels, it will be quite easy to understand why the second example compiles after this slide. Okay? So if we go by the definitions, we can assign scope levels to all the variables. So I is global variable according to rule number 1 is in scope level 1. Putting error in is a built-in function by definition that's in level 1. So that's in level 1. And also foo is a function declaration. If we look at the rule number 1, that's also in level 1. That's it. So we have scope levels for the first 3 entries. Now, so as you can see here, there is a opening brace that opens a new scope. Okay, so here we are at level 1. Once we move inside, we will be at a level 2. That's why this I will be at a level 2. J will be at a level 2. Now we open another scope. So we need to increment the level by 1. So this pink I will be at a level 3. Okay, so that's for the scope level. That's also why, as you will see later on, here we use I, we know that's related to this I instead of that. Okay, that's something I'm going to show you, just maybe hover. This example is a little bit confusing before. So somebody says it doesn't compile, actually compiles. Now if you try to assign scope levels to all these identifiers, it should be very easy to understand why this compiles by the C compiler. So by definition, foo is a function that's at level 1. All the built-in functions by definition are initially at level 1, so we have level 1. Now, here there is a parameter declaration. Remember, when you have a parameter declaration, those parameters are regarded as being declared in the body of the function. Okay, if that's the case, when you see this full yellow color, that will be at level 2, because you increment the scope level by 1, because this full will be regarded as declared inside. So as you can see here, even we have 2 occurrences of full that actually have different scopes with different scope levels. That's why compiler couldn't get confused, which is which. So inside here, we open another scope. Okay? Put integer array. That put integer array is at level 3. Okay? Because initially it's at level 1. Once we're here, we increment that by 1, that's 2. Here is 3. So here we have a redeclaration of the same variable, but that variable gets the scope level 3. Therefore, even you see the same variable being declared many times, as long as they are in different scopes, okay, they are different variables. They are all 4. Okay. So that's why if you compile this code by the C compiler, it actually compiles. Okay. Any question? No? So, these are the scope rules. And if you are a bit rusty, it might be a good idea if you just revise your knowledge, scope rules, high-level programming languages. You don't have to memorize all these. But what's more important here, you have to understand they are the scope rules, determining how variables are related to a declaration. So, now we can move to identification. So once we know the scope rules, we can do the identification. What that really does is to look through the code for every use of a variable. We need to find its corresponding declaration. Because there's a variable here. So where is this guy's declaration? Oh, that's all I do. So we do that sometimes by using a single table. That's just auxiliary data structure. Here we talk about attributes of identifier. And hopefully you have already started working on parser, or you have submitted, or you're in the middle of doing that. That means you are trying to build a tree for a DC program. Remember, in the tree representation, for every variable declaration, there's a declaration node. Every time you want to use a variable, there's a node showing there's a use. So here then we talk about attributes of identifier here, because eventually in the last assignment you're going to see more attributes. Here's the thing we are interested in. We really just, for example, if it's a variable function declaration, we'll be interested in its type. Let's say whether it's a function, whether it's a variable. So there are two different ways of doing the identification. So one is you simply just modify the tree. Remember, in the current tree you have created, you're creating, there's no connection between a variable used and its corresponding declaration. So one way of doing the identification is simply just to modify the tree and then link every use with a pointer to its corresponding declaration. Okay. So if we take a look at the
Hello? No. Oh, I didn't. Let me see. Yeah. Yeah. Why did you give 2,000? Hello. Good. I had a sore throat this week. I don't know. I'm not sure. Yeah, it's enough. No. 100%. Mm. Mm-hmm. It's pretty easy this time, yeah. Yeah, or maybe it's just because I'm getting smarter. Yeah, I worked 9 hours last week. So $600. Yeah. Yeah, a little bit. Yeah, it's okay. Mm. Not sure, not sure. Mm. Did she finish that? Did she post it yet? Mm. Oh yeah. I cooked chicken and rice. Yeah. Ah, I don't know. I haven't. I tried to go to 3 different groceries. They all not have eggs. Yeah. Mm-mm. Yeah. Mm. Yeah. I'll try to come. Mm-mm. I think sometimes it's a better deal. Sometimes, yeah. A little bit, yeah. Yeah. Mm. I don't have ginger. I'll need it back. I don't. Too lazy. I'm almost recovered. Mm. Hmm? Hmm? Uh, not sure. Forgot. If the skin looks like that, it's fine. I don't care. Mm. Mm. The what for free? Mm. 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 What? Is Jonathan there? Ah. Mm. Mm. Yeah. Mm. Yeah. Oh, maybe. Yeah. Mm. Maybe. Yeah. Yeah. Brian already did like 4. Mm. Mm-hmm. Mm. Mm-hmm. Mm. Mm-hmm. said you paid. Hello. You said you paid for the laptop, but you also put $2,000 as well. Huh? Oh. No. Oh. Okay. From where? No, they said they're still processing it. Not sure. Yeah. Okay. Yeah. Mm-hmm. Yeah. Okay, I will. Yeah. Okay. Bye bye.
You can see every time you see a variable use, you need to create an ident node. Here there is a field called decoration. So that deco is a pointer that will be eventually, well, in assignment 4, using our starter code, that pointer is going to be linked with this corresponding decoration. Okay. Of course, now that approach is you just maintain the information side. But in our assignment, assignment 4, we're simply just going to link this two together. Okay, we saw that already because in this case class, by which you can build identifier node, there is already a technical pointer that's going to point to its corresponding decoration. The moment is now, because the process isn't done in here. That's the job of the cloud checker. So we're going to do the identification by using some auxiliary classes. This will be the classes you will see in assignment 4. They're very small. I'm not going to really look through the too much. Compute identifier node. There's already a technical pointer. That's going to point to its corresponding decoration. The moment is now, because the process isn't done in here. That's the job of the cloud checker. So we're going to do the identification by using some auxiliary classes. this will be the classes you will see in the example. They're very small. I'm not going to really look through the code much. Just to understand the concept, that's sufficient just to say the functionalities. For example, here, in the symbol table, you understand this shortly because I'm going to go through examples. Okay? So every time when we see a declaration, we're going to represent that by recording its name, scope level, and the pointer to its corresponding declaration. But we'll see this shortly. Okay? And to manipulate the symbol table, there are a few functions. These functions, quite boring, I'm not going to go mention them, but you will see that when I go through the examples. Open scope has just one line of code. Okay? Every time we move from one scope to a nested scope, which is simply increment a global variable. Well, since we are talking about it, that is very easy. Okay, here's the implementation for open scope. So there's a global variable called level that remembers level of the scope we are processing. Every time you go from one scope to a nested scope, you just increment that by one. That's open scope. Closed scope simply means we have processed everything in the current scope. We're just about to exit from the closing brace. Then you can assume everything right in that scope. Okay? So you see the code here that basically just deletes everything in that current scope. Insert and retrieve is very simple. We need to record all the declarations we have seen so far to put them in the simple table. Okay. Now, next time when we see a variable used, we're going to search the table to see whether it is there. That's called a retrieve. So once I go through a small example for this, will be understood. Okay. You can take a look at this yourself. So study environment, for every language, there is a study environment. That's why in one of the examples I show you, remember the example with India? I ask you whether this compiles or not. Okay. That is related to so-called study environment for a language. So basically every language provides a set of default functions, libraries, global variables, and all that stuff. But how does the language make these things available to you? Okay? You can do it in many different ways. Then you have to define the scope as well. Okay? So that's the study environment. And when we do the identification, because we have built-in functions. Remember when you do a parser, you're not going to see the tree representation of this built-in function because they're not part of the code, the application itself. Okay, so in order to do that identification, we simply just create a lot of small trees. Then we fill the table initially and make this function available, and then we can do the identification. Anyway, there's an example for you to understand. For example, put integer array is a built-in function. That's not part of your application. You don't see this tree. And we simply just create a tree first. Now we fill that table by leaving a pointer to this guy. So next time when we see a call to this function, we're going to search through the table. If it's in the table, we know, okay, that's available. Otherwise, you can require error. Okay? Just very simple. I'm going to go through this example, okay, to help you understand everything we have introduced so far. And this example is very simple. As you can see, we have a function for. Inside that function, we declare I as a variable. Then we call put integer array. Obviously, we're going to print the value of this I, not this I. Now, in a inner scope, that I is redeclared. Based on your understanding about high-level programming languages, we all know this I should be related to this I, not this one. Okay? Because we do that according to the scope rule. Once we are outside this scope, we have another call to put integer array. And obviously, this I is going to relate to this I, not one unit. Okay? So now, our identification process is just to explicitly link every use of these variables to its corresponding declaration. What are uses? That's a use. That's another use. Okay, when we say a variable use, we simply talk about a reference to a variable, to identify. You have to use a variable, you call a function, that's called use. And here is called declaration. That's a declaration of the function, that's another redeclaration of the variable in the scope. Okay, we have already created a small tree, so that we can do the identification. Okay, so that's the result, but I'm going to go through this here. don't know how well you can see it. Can you actually see it? Very small. Okay. Maybe I can just, I don't have to plug the system. So it might be also easier if I have some animation here. I might just put it here. Because I want to go slowly. Okay. It should be fine. Alright. So, I want you to do it this fast. It's not very difficult to understand. So we go to our application, and there's a simple table to show here. So we have our ID, we have a scope, level, we have attribute. I'm going to write down here, but actually you're going to see the animation there. And we start with a variable for the level, because by definition, the outermost scope, everything in that scope starts at the level 1. Okay? So that's sort of a empty simple table which I started initially. Okay? Now we have to come back because I can't use it too small. Okay? You see that one I have to call out. That's the empty table. So on the top right, that's a lot of small trees created for one of each of the building functions. So during the initialization, we actually insert an entry into the table. We say put integer in is a building function. By definition, it should be available as scope 1. Attribute is filled with a pointer pointing to the corresponding declaration. Okay. Remember, we have quite a few building functions. If you look at the starter code, we insert one for each of those building functions in the same way. Okay. Here there is only one. One building, which is good. That's it. Okay. So remember the level at the moment, the global variable, this guy is 1. Okay. So now we are going to traverse the tree. Your parser creates. Well, your parser is created because by the time we did run the checker, the parser has already created tree for us. We're going to start from the root of the tree. Can you actually see this? I mean, that's the largest possible. But anyway, that's so we start from the root of the tree here, and we are going to do the identification. Okay. So when we start from here, we're going to move to here. So let me just that is the code. Okay, this is the tree. And now if you see the tree, you should be able to see where we are. We start from here. We're going to do a post-order traversal, post-order inverter altogether. Then we're going to move to this node. Then we see something called function declaration. Why? Because this is this one. Okay? So we see a function declaration. Every time we see a declaration, we're going to create entry in the table to say, hey, we have found a declaration. Okay? So we initially remember we did that. So now we are going to insert an entry saying we have found a function declaration 4 at level 1, and we add a pointer pointing to this one. That's it. Okay? So we are about here. Okay? Now we're going to move inside. So here there's a compound statement. So basically we are going to move inside. So once we move inside, we see a compound statement. We're going to call open scope. The open scope, all the open, I just get rid of this. Okay? The open scope, all the open scope is going to do is, remember the moment is 1, it's going to increment this by 1. So that means we're going to render a scope which is scope level 2. So now we're going to move down here. Okay? Now we see a local variable. Now we see this part. Okay? Since it is a declaration, we are going to insert into the text. This time we say we have found where are we? Yeah. So we have found a second declaration. We said this guy's at the scope 2. We leave a pointer pointing to that guy. Okay. So far, we have just found a second declaration. So once we're done that, we're going to move to this part of the tree. We will be here. Okay. What this is all the way. We're going to come here. What is this? We're going to see this call integer in. So that is a use of identifier. Okay. So once we see a use, we want to find its corresponding declaration. How do we do that? Just search the table backwards. Okay. The most recent one is your corresponding declaration. So we search the table backwards. We're going to try to find this guy's declaration. Well, all the way here we found this guy. That must be the declaration for the first call. Then we do the first declaration. We say, hey, this is use. I'm going to annotate your declaration. Okay. So, where are we? Yeah. So we have found a second declaration. We said this guy's at the scope 2. We leave a pointer pointing to that guy. Okay. So far, we have just found a second declaration. So once we're done that, we're going to move to this part of the tree. We will be here. Okay. What this is all the way. We're going to come here. What is this? We're going to see this call integer in. So that is a use of identifier. Okay. So once we see a use, we want to find its corresponding declaration. How do we do that? Just search the table backwards. The most recent one is your corresponding declaration. So we search the table backwards. We're going to try to find this guy's declaration. Well, all the way here we found this guy. That must be the declaration for the first call. Then we do the first declaration. We say, hey, this is use. I'm going to annotate your field. Remember this field here? So this field. So, yeah. So we are going to say that's your corresponding declaration. So once we have done that, we're going to move this way, push auto traversal, and we say I. What is I? That one. Okay. So we're going to say another use of I. But again, you just search the table backwards, and you know obviously that I has this declaration right here in the table. Then you just say this I is related to that declaration. If you look at the code, it says this I is linked to this declaration. It's just as simple as that. Now, we have finished. we've done that bit. We finish this bit, we move here, but immediately here there's a compound study. So that means we're just about to enter this new school. Okay? Now we're gonna for open scope beginning from this point here. So now we can enter scope at level 3. So once we enter that scope, we move all the way down here. Now we see another D. Now we see R. There is a compound study. So that means we're just about to enter declaration. Which one is that? This one. Now we do the same thing. Since it's a new declaration, we enter it into the table, that's at scope 3. There's a pointer pointing to its corresponding declaration. As you can see, even if the same variable has been declared twice, they have different scope levels. We should be able to know which is which. Okay? So that means we have processed which one? We have just processed this declaration. We're going to move this to this way. Now we're going to move this way. Now we see put integer array. That's this one. Okay. Again, we just search through the table and we should be able to know what's the corresponding declaration for this guy. Okay. It's the same one. Then, as you can see, we just link this guy to its corresponding declaration. Okay. So we've done that one. Okay. So we have processed this one. Now we're going to move to from here all the way. We see another I. This is this guy. Okay. So this time we're going to search the table bottom up. Okay. Now you're going to see this I, but not the second last one. So therefore, we are going to relate this I to this, not to that, because we always search the table backwards. Okay. So now, as you see, we link this use to its declaration in the same scope, in the dash line. Okay. So once we have done that, as you can see, we are just about to exit from this scope. And from the tree, you can see that too. And once we've done that, we can just leave this bit. That's a compound statement. We're going to just leave here. Now we're going to call closed scope. When we call closed scope, we're going to decrement that by 1. We're going to leave that scope at level 3. So that gets decreased by 1. At the same time, we need to delete everything we have inserted into the into the previous scope because we just processed it. So everything that is scope level 3 will be deleted. So basically, this declaration has been deleted. Okay? Now see there's one more call to deal with. Now we're going to move to this bit. We're going to see here. That is the representation for the last call statement. As you can see, previously we had deleted the declaration for the I, the innermost scope that's gone. Now we see put integer. Again, we search through the table, we found that one. So we link the use to its corresponding declaration. Finally, we're going to see another I, this I. As you can see now, we're going to find easily this I is related to that declaration, but not this one. So this is very simple because we've done it in this sort of a way according to the scope rules in VC. We always traverse the tree in sort of this way. Therefore, we can always link a variable use with its closest declaration. Now, going back to this example again, we have one use of I here, but two declarations. Since this is declared in an inner scope, therefore that declaration is hidden. There's no way you can access it. I don't know how much familiar you are with C++. So that's why in C++ you have this so-called scope resolution operator, which allows you to access a variable in outer scope. Okay, all these syntax rules have to be introduced in order for you to access that variable. In VC, there's no way for us to access the first declaration once we are inside the inner scope, because there's just no mechanism provided in C and VC. So that's pretty much the identification process. Is that clear to you guys? Okay, so just to summarize, static analysis involves two sort of stages. But these two stages are actually done together. One is called identification, in which we make use of the scope rules to link every variable used with its corresponding declaration. In assignment 4, we do that by decorating the tree. You have already seen from these animations. So by the time we have finished the identification, every variable used will be linked with that corresponding declaration. Your job, as I will explain tomorrow, is to implement a type checker that just enforces all the type rules. That has already been implemented, but that's done together with your type checker. So for example, by the time you are trying to see what this guy's type is, well, it should have already been linked. When you do your type checks, you want to see, hey, what is the type of I? You traverse the point out, you see the corresponding declaration. From the corresponding declaration here, you see that I has been declared integer. So that's pretty much how you're going to make use of this information. But that, again, that part has been done. Okay, so this lecture is it's not very long. Just to summarize, if you haven't finished your assignment 3, it might be a good idea. You should try to make sure you can finish it as soon as possible. Tomorrow we're going to talk about how to make use of type rules to do the type checks in assignment 4. The specification will be released before the break. And basically by the time we come back, we will just have like 2 weeks dealing with code generation. We need to talk about JVM, just assembly instructions, then the technique we're going to use to implement a code generator. Then we do a few, 1 or 2 lectures, finishing what we did not finish in the first 2 weeks, like AFA to DFA conversion and error runtime or different parts. So, do you have any questions? All right, okay, that's all for today. See you tomorrow then.
How is this guy doing 1 hour lectures every lecture? What the heck? Okay.
Okay, good afternoon. Again, this will be a relatively short lecture. So we will look at
How are they doing
this
4
week.
short
we
lectures in a
will
row?
start studying
Crazy work.
analysis. Yesterday, I explained how we can. A static analysis involves 2 different classes or phrases. So one is called identification. In the identification phrase, we try to relate every variable used to its corresponding declaration. That's what we did yesterday. The other task is something you're going to do in assignment 4. Other task is type checking. So in assignment 4, once you have built the tree, in assignment 3, you're going to implement a visitor as a concrete implementation of the visitor interface. You're going to traverse the tree, decorate the tree in the sense that you're going to annotate every expression with its type. you know, that's pretty much what you're doing. Of course, by doing that, you're going to also report some error messages. So I mentioned these two test cases you're going to get, which contains just almost like one error per line. It doesn't hurt if we just go through some of this. So basically, as you can see, we have declared a variable to have the type void. Okay, and here we have Boolean variable. We have a function that takes, 4 parameters. Somehow here we have an array with elements. Element type is void. Then this is legal in C, but not in VC, because in VC we have just taken that feature from Java. In VC, every Boolean expression has to be defined, basically it's defined in terms of the Java notation. You have to use true and false. Anything that can evaluate true and false to build a conditional expression, Boolean expressions. And certainly that's not syntactically correct. You cannot assign false to I because I is the integer variable. 2 plus true is not okay because they have incompatible types. Return 1.1 is disallowed because the function only allows you to return an integer. And the I here alone, that's okay because I is integer. So here this statement is legal in C because in C anything that's not 0 can be used as true, anything that's 0 can be used as false, but we did not allow that in VC. Again, there's issue here. And G here we have an expression. I is a variable, but it has been used as an array. H, so there's no definition for that. And G, you notice where G is no corresponding declaration for G. And here we call F by passing four values. However, this call is not semantically correct because the function expects the first one to be integer. We have passed just a floating point value instead. It's not allowed. Again, this guy expects 4 arguments to be passed in. We have just passed 1 too many. Yeah? And bracket continue can only be contained inside loops. So in assignment 3, our parser is happy with passing all this. I remember, let's just try. So the parser is happy with all this because pretty much every line has a semantic error. So that highlights again the differences between syntax and semantics. Because some students sometimes ask questions early on, say, look, now what's the point of having a grammar that allows this? That looks silly, because we should have developed a better CFG that can sort of eliminate quite a few of those. So what's the point of having all these semantically illegal statements to be carried over all the way to the checker? The answer is very simple. Okay? If you try to use a more complex CFG, certainly you can eliminate some of these semantic errors. But you make your CFG more complex, number 1. Number 2, when you have a type checker, all these errors can be caught anyway by a type checker. Even you use a more complex CFG to get rid of some of these semantic errors, that wouldn't simplify your checker either. You have to still write pretty much the same amount of code looking for all the possibilities. How do you know? People will write all this stuff. So it doesn't save you much. So the second one, just a lot of errors related to array. For example, we look here, we index into X by using a string that's not allowed. X, a bunch of things. Here, for example, A is just a variable, but we have initialized that with an array expression. And here we've got too many elements to initialize X, which only expects 2. And this one is okay. Then we have this guy is an array, but we initialize that array as if it were just a variable. All these errors. Again, if we run our parser, and there's no syntactical violations at all. So all right, so that's the other one you saw yesterday. Pretty much we're going to finish the static analysis. We're going to have a break. During the break, of course, there will be no lectures, no tutorials. After we'll come back, we're going to spend a week looking at the assembly language we're going to use, because the first 2 weeks after we come back, we pretty much are going to do a few lectures preparing you to implement the last assignment. Okay, that's a code generator. Since we're going to implement a code generator, we have to talk about the assembly language we're going to use because we're going to translate VC into that assembly language. So we need to look at the instructions, the stuff we need to know. Then in the second week after the break, we're going to look at a very simple algorithm we're going to use to write a code generator. So you saw this slide before. I also summarized static analysis, 2 components. Identification, you make use of scope rules to relate variable uses to their declarations. When you write a type checker, you make use of another set of rules called type rules. Okay, you make use of type rules to perform all sorts of type-related checks. Okay? And again, in assignment 4, your type checker is going to be a visitor. So that means you need to implement all the methods in the visitor interface, one for each of them, so that you can process each distinct type of tree nodes. Where are we? Okay. So I just want to say a few words about static and dynamic scopes. Have you guys have any experience with this dynamic scoping? Static scope, we talk about scope. I mean, scope of declaration is really just part of the code in which that declaration makes sense. That declaration is valid, you can use it. And so many languages nowadays are static scope. Of course, there are also some languages which also support dynamic scoping. It's not something we talk about here today. I just want to highlight, there are these 2 types of scoping. In some sort of industry languages, it's mainly static scoping supported. And they have their own sort of advantages and disadvantages. I'll just show you an example. So if you look at this code, you can consider this as a VC program or also a C program. But suppose we apply dynamic scoping, you can see the outputs will be different. So if you apply dynamic scoping, the output from this program will be 1 and 2. Okay? That's because first time in the main we call G, then the G in the middle will print I. Okay? In dynamic scoping, the binding is basically how do we do the identification? We cannot do it statically anymore. Okay? We have to do it dynamically by using the call stack. Essentially, dynamically, you look at the sequence calls you make towards that print statement. Then you look at this chain of calls, you find the most recent declaration along the call chain. So from main we call G, then we're going to print I. So dynamically we look back at all the callers. Okay, who is the caller of G is the main. Okay, then I is declared there, so we're going to print 1. The second time we're going to call F. When we call F, I is initialized to 2, then F calls G. But now, when the G is called the second time, we're also going to look back at the chain of calls reaching G. So the most recent one is obviously F. Then you find a declaration. So that happens to be 2. So in this case, you print 1 and 2. So if case, you print 1 and 2. So like second time, we're also going to look back at the chain of calls reaching G. So the most recent one is obviously F. Then you find a declaration. So that happens to be 2. So in this case, you print 1 and 2. So if so this is this program in C. So if I run this C program, what do you think the output will be? So if we compile this, it's the same program. Actually, we see 3 and 3 printed. Actually, if you look at the code, it's not going to be hard to understand because in static scoping, and the identification can be done statically. So that means when we do the identification on this code, and we look at this print statement, and we need to find where this guy's the i's corresponding declaration is. Because if we look at this print statement here, then the corresponding declaration must be this one. So therefore, every time one of these guys is called, the compiler is going to relate this use of I to this declaration, okay? Regardless how G is called, okay? So now you probably see roughly the advantages and disadvantages between static and dynamic scoping. Modern languages, many of them use the static scoping because everything can be statically knowing, like types. You can develop a lot of software tools to analyze your implementation to improve safety, security, because a lot of things are known statically. But if you apply dynamic scoping, suddenly you add a few calls in between, everything can become very different. So that's just for your information. So we talk about type checking. And surprisingly, type checking is very simple. There's really not much to say. So I just go through the basics, and the specification will be made available tomorrow, and you can start working on that. So when we do type checking, first we need to understand what type is. Whenever we speak of type, we talk about two sets. We talk about two sets. Firstly, a set of values. Secondly, a set of operations. You talk about Boolean type in Java. So what are the two sets? So firstly, you have a set of values, which contains 2 and 4, only 2. Then you have a bunch of operations you can apply to that, and, or, all this stuff. Okay? For every type, okay, you can talk about these two sets. A set of values and a set of operations that can be applied. To those values. As far as our language is concerned, so we do type checks. We make sure all expressions are well formed. And we also do some flow of control checks required by the language. For example, if you see something cannot put break and continue outside the loop, it doesn't make any sense. And this can be checked easily. Using just a few lines of code. We don't have switch statements, but if we did have switch statements, we also would need to check for the uniqueness of all the labels. You cannot have several labels with the same value. It doesn't make any sense. What are the type rules? It's basically just a set of rules for us to infer the type of every language construct. Okay? Then we decide whether that construct has a value type allowed by the language. So type checking is just a process of applying the rules. Just do all checks, type checks. So if you see, the checks are very simple because it's easy static type, and we don't have any structs. A lot of checks are very simple. A lot of your work will really be spent on just type checking expressions. Just make sure every expression is well formed. All the other checks are very simple. Break and continue. Every time you see them not inside a loop, you got to report the error. And obviously, you have a function. You have to make sure every return is assignment compatible. I mentioned this in the first example. If you have a function that has a integer return type, you certainly cannot represent a string. You can return a float or boolean or that to make sure that assignment compatible. And there are some other checks which are optional, like unreachable statements. This is because in order to perform these sort of checks, you normally need to do some data flow analysis. That's something I used to do in my advanced compiler course, and this is also something people do in their research. For example, in my group, we have a few PhD students working on how to develop program analysis techniques just to make sure to find bugs, security vulnerabilities in programs. All these programs have been compiled successfully by the compiler, but they have various all sorts of problems, like use of the free. You must have heard a lot of this, double free for C and all this stuff. For unreachable statements, it's optional, and that's mentioned in the specification. The reason it's optional because we haven't done any data flow analysis. There's no point of hacking that. And once you know what data flow analysis is, that can be easily formulated as a data flow analysis problem. So this is just so much the theory we are talking about. So what's the sort of type checking process? Pretty much, if you look at a unary operator, which takes a single operand and returns one result, if a binary operator that takes 2 operands and returns the result. Obviously, for the binary operator, you have 3 different types. Okay? So you can specify the first one to take something of type T1, second one has to be T2, then it returns something as T3. Okay? So basically, we need to check if the operator is applied to compatible operands. So for example, if we have a function declaration like that, okay, and this will be the signature. So essentially, int is T1, and float will be T2, then this int will be T3. So essentially, we say the compiler infers expression E has some type T, or that E is ill type. Okay, it's just, let me just read this. It's very simple. If E occurs in a context where T prime is expected, then the compiler checks to see if both are equivalent. Okay, what does this mean? So let me just write down this function here. We have so basically we have a function. Okay. So the signature of this function, as you can see, T3, and this is int, that is a float, and that is int. Okay. So basically we have a function declaration. We have 3 different types: T1, T2, T3. That's sort of a types expected. Now coming back to this slide, what are we talking about here? Basically, this is what it says. So this is a function declaration, but suppose somewhere you have a call. Okay, so you want to call this function. Okay, coming back to this. It says you see expression E. Okay, you want to deduce its type. Then you make sure that in that particular place you see that E, you want to make sure that has the type expected. Okay, so here we see this guy. So we have E here. Okay, the 1 is E. That's your expression. Firstly, we need to deduce 1's type, integer. So we deduce the type is integer. Now, to know whether this expression is good or not, you've got to look at the environment in which this expression appears. Where does this expression appear? It appears in your call expression. Then you look at the corresponding declaration. Okay, is this integer assignable to that T? Essentially, you find the type of the expression, you need to make sure that that expression has the type expected in that environment. Okay, certainly this is okay because we want to see an integer. Now you have passed the integer to that. That's okay, good. Now, if we look at the second case, that's also good. Look at 2.3, you deduce its type is a float. Is float okay? Is this call? Yes. You look at the signature of the function, that's fine. Okay, that's good too. However, if we change this example a little bit, we just swap this to 2.3. Okay, we're going to call f by passing a floating point value and an integer. Now we look at this guy as a E. So firstly, we need to deduce the type for 2.3. So it's a float. Now to know whether float is allowed or not, we need to look at the corresponding declaration here. Okay, and if you look at the first parameter of the function, that guy expects an integer, but now we're going to pass a floating point value instead. Is that okay? Well, you have to look at the type rule. And if you look at the type rules of VC, one of the rules says no, this is not allowed. Because in VC, you cannot assign an integer value to a variable declared to have the type integer. Other way is okay, but not this way. Okay, so coming back to here, so basically that's what the type checking is. Whenever you see expression, you try to deduce its type. Okay, so then you see if E occurs in a context where T prime is expected, you have to make sure this is equivalent. What that means is we have just done the first one, 2.3, 1. Now we look at this guy as E. Okay, that's our E now. So this time we're going to ask the same question. What's the type of 1? Well, it's integer. So this is our type. Now, what is the expected type? It's a float. They are different. But are they equivalent? Equivalent in the sense that can an integer be considered as a float in this context? The answer is yes, according to the rules of VC. You can certainly assign an integer value to a variable of type of float. So coming back to here, that's what it says. If E occurs in a context where T prime is expected, the compiler needs to check to make sure both are equivalent. Okay? So in this case, yes, they're equivalent, but if the other way around, it's not equivalent. Okay? That's all we are doing. So, any questions? Now, in order to do type checking, we have some fields inside our ASC classes. If you take a look at this expression class, which is abstract, that has a hidden field, well, hidden in the sense that you do not know yet. It has a field called type. At the moment, your parser hasn't done anything to that, so there's a left to be now. What your type checker is going to do is going to give that type field the correct type for any expression you see on the tree. Okay, so this is abstract class. We have many concrete expression types, remember binary expressions, integer expressions, they're all subclasses. So that means every expression node has a type field. That's going to be decided by your type checker. Similarly, we also have variables. A variable can also have a type, so there's a field there as well. You need to also assign a type to that. That's very easy. Remember the identification I did yesterday? Given the identification being done at the same time, you know every time you see a variable, you can use the pointer to reach its corresponding declaration, from where you can just deduce the type straight away. So that's this one. Okay. Now, type checks, just like code generation, are typically done in a bottom-up manner, because we normally need to, when we try to work out the type of a given expression, we normally need to find the types of the smaller expressions forming the larger expression. You typically work inside out. But here, every expression has a tree representation. So how do we do it inside out? Well, pretty much we just traverse the tree in the post-order traverse. When you see the leaves, you deduce their types. Then you just work your way upwards. Eventually, you deduce the type of the largest expression. Okay? So basically, that's it. So remember, the type check is a visitor. When the visitor sees a literal, a constant, it knows the type straight away, as I have just done for you. Every time you see 1, you know its type. You see 2.3, you know the type. That's very easy. Every time I see an identifier, you follow its pointer to reach its corresponding declaration. That's done in yesterday's lecture. Now, whenever you see a binary expression, okay, you try to deduce the types for its 2 operand expressions. Then you try to apply the type rules to see whether the entire expression is well typed or not. Of course, once you know how to work out the type checking for binary expressions, the same idea goes for unary. Actually, a lot of your time will be just spent on just this one visitor method, that's visitor binary expression. Okay? If you write that nicely, sometimes 30, 40 lines of code will do, then you should be able to type check all binary expressions. Once you have done that, you cut past your code, and then you deal with the binary expressions, the same idea, just one operand, and that will be done. So in assignment 4, since we do type checks, some types have been defined for you. They're just a bunch of objects, integer type, float type, all this stuff. So basically, you use them every time you see the integer, that's the type. We also have an error type, because some expressions are not well formed. They don't have a legal type. In that case, you give that guy error type. Okay. Remember, in the visitor design pattern, every visitor expects some information to be passed in as inherited attributes, and even return to somebody else. You can return that as a synthesized attribute. There's not much to pass in, but mostly you pass some information outside from your code. There are only a few occasions you need to think about how to do it the best way possible. Otherwise, everything else is really straightforward. So this slide actually summarizes what I meant just 2 slides ago. Here are a few visitor methods already implemented for you. Okay, we do a post-order traversal, remember, eventually we're going to hit all the leaves. Every time you see identifier, that's the code. Okay, you see identifier, you follow its binding. The binding is just a pointer pointing to its corresponding declaration, you get its type. You see a constant, you know its type straight away. If you are visiting integer, what's its type? Integer. You see a float, it's a float type. Boolean, string, so on and so. Okay, pretty much. Okay, there's one thing I want to talk about, it's called type coercions. And some students just got confused about this. So basically, we need to understand that in high-level languages, all these operators are overloaded. Okay? Because we are familiar with Java, we know what overloading is. And because the overloading is good, because we can actually write plus 1, 2, plus 1 point, I just use infix notation because plus is a function. You just can do all these sort of combinations. Essentially, we abuse, in a way, the notation so that we can use the plus to deal with 4 different combinations, with 4 let's say we don't have float and integer types, okay? So effectively, we say the plus is overloaded because the plus is a function. That function has 4 different signatures. And you have 4 versions of that function. It's just that we probably did not pay much attention to. That just simplifies the programming. However, at the hardware level, a plus is not overloaded. Okay? You either have an instruction that adds 2 integers, or you have an instruction that adds 2 floats. You don't have an instruction that adds a floating point value and an integer value. It doesn't make any sense. I don't know how much we are familiar with hardware. So either they are floating point values or they are integer values. You can't mix them at the hardware level because we don't have those instructions. So that's why here we talk about type coercions, because all these operators are overloaded. So that means another task you need to perform when you implement your type checker is to resolve all these overloaded operators. Okay, I don't know whether you finish your parser or not, because if we have 1 plus 2, if you look at the tree from your parser, you see plus. Okay, however, after type checking, we don't want to see plus anymore. We want to see either I plus or want to see either F plus. That means we want to indicate clearly this plus is an integer addition, that plus is a floating point addition. Okay, we have to distinguish between these 2. That's what you will do in your type check as well. Okay, type coercion in high-level languages simply means we convert a type into a wider type, in the sense that we don't lose any precision. So when you convert integer to a float, not the other way around. Okay, one is called coercion, other one is called conversion. Okay, we talk about coercions. Okay, so this will be done also by your type checker as well. So having said all that, if we take a look at the example, everything will be really clear. So that's the example. Very simple. With 2 variables, I has the type integer, F has the type float, and we have expression there. You know straight away the right-hand expression evaluates to a value as a float in CFDC. However, the floating point value cannot be assigned to I, to integer. So eventually there will be 1 error message reported by your type checker. Okay, let's see how this is done. So if we try to, so basically we run the parser on this example. Then the parser is going to build a tree representation. It's basically a program. It's a lot of declarations. You have this sort of a local declaration there, another one. So eventually, remember this is a that declaration, another declaration. So this is for I, that's for float. That's where assignment is. Okay. So now, once we see the tree, we don't care about the rest. Let's just look at this part. So that's the part where that single assignment is represented. Okay. So how do we do the type checks? You would pretty much just do a post order bottom order traversal. So we traverse the tree, and eventually during the post order traversal, we're going to see the first I. Let me just use the pointer here. Okay. So the post order traversal, starting from here, going all the way here, we see I. Then we need to know its type. Well, by the time we see I, this guy is called because it's a visitor. Once this guy is called, you can get the type from the pointer pointing to its declaration. You get that straight away. Then we know I has the type integer. Now during the post order traversal, we're going to eventually reach here. Okay, this is this guy. Then the same visitor method is called again. We're going to know again its type is integer. Now we're going to move to this bit. We see number 1. Okay, whenever we see number 1, this visitor method is called. We know its type is integer. We just say, look, this guy has integer type. So this guy gets type integer. Now, one operand has type integer, other one has integer. And according to the type rules in VC, this larger expression, which is this one, multiplication, will be typed as integer. So we have the integer type here. What that means is, so that expression's type field will be assigned integer. Then we do the same thing. Eventually we are here. Then we see F. When we see F, this guy is called again. We're going to retrieve its declaration. We're going to go to its declaration, get its type. So pretty much, if you look at the code here, again. So once we're here, there's a pointer pointing to here. Okay, that's what we did yesterday. Then you see this guy's type here. Just get it. Then you know float has type float. Now look, we're going to type check this expression. The left operand has type int. The right operand has type float. So according to the type rules of VC, which is the same as in C, this guy will have the float type because one is int, one is float. Remember, all these operators are overloaded. I said here already. Okay, in high-level languages, it's perfect legal. We type this as a float. Now we look at this assignment. Left side has the type integer. Right-hand side is type float. Now we look at the type rules from VC, which says that's not allowed because it's called assignment incompatible. You cannot assign init float to an integer variable. Then just report error. Okay? So this slide highlights the basic idea behind type checking. You do a bottom-up traversal every time you see an ID. You retrieve its corresponding type from the identification phase. The code for that is being done. You don't have to do anything. Every time you see constants, you know the type straight away. Then you apply type rules bottom up. Then you deduce types for small expressions. Then you work out, dealing with the larger and large expressions until you eventually know the types for everything. You report errors along the way. That's pretty much what we do. Okay. So again, in this course I mentioned before, we don't deal with errors. I mean, we don't deal with errors in the sense that we don't have a module that handles that. Every time we talk about errors, there are three issues you have to deal with: detection, reporting, recovery. So you want to detect where the errors are. You want to report an error message that should be as accurate as possible. Finally, you want to recover from the error so that you can report more errors. So here I have an example showing you how to reduce spurious errors. However, you will not be penalized if you print spurious errors. So if you look at this expression, true plus 1 plus 2. So your parser is going to build a tree like that. Okay? Since we do type checking by performing a post-order traversal, so when we see true plus 1, and immediately we realize this part of the expression, this sub-expression, is not well typed. Okay? So then we need to assign this guy a sort of error type. Right? So when you assign error type to this guy, then everything else that it uses that indirectly or directly cannot be well typed. So even though this is integer, now we end up with asking whether it is okay to add something that has an error type to an integer. Okay? So obviously you can report another error saying, look, the second plus also sucks. Okay, it doesn't work. Okay? We just use very simple techniques to reduce this sort of spurious errors. But once again, you're not penalized for printing spurious errors. So you might want to take a look at the sort of implementation here. Here, just only a few lines. These are just simple hacking techniques we use to avoid reporting too many spurious errors. So often we need to check to see whether one guy is assignment compatible to the other. That means whether the right-hand side can be assigned to the left-hand side. Okay? And that's how we implement this. And we also need to check whether these two guys have the same time, equivalent time. As you can see, as long as you want to check to see whether one type is equivalent to the other, if the other one is the error type, we simply say that's fine. Okay? What that means is, coming back to, you can take a look at yourself, just one line each. Basically, what this means is, somewhere here we need to check whether these two types are compatible. Now, if you call those functions, ask them, are these compatible? And they're going to cheat on you, saying, look, yes. So that you're not going to report any further errors. Okay? It's just like that. But once again, I want to emphasize again, you're allowed to print spurious errors. Once again, all the test cases we use for marking assignment for will be small. Each is typically designed to have one error. We are only interested in that error. Once you see many other spurious errors, we really don't care. Okay? Maybe I just want to answer a question maybe somebody will eventually ask. For example, in most of the test cases we're going to use, each case has one error, and that error message is pretty much unique. Okay? Only in very few exceptional cases, okay, there might be some other messages that will make sense. For example, we have a function declaration that expects one argument. Then we simply have a test case that calls that by passing 2. I mean, in this case, there's just one error message you have to use. We have that. I'm going to talk about it later. It's like calling a function with too many arguments, something like that. Because that's acceptable. But if you print the other error message, you pass in 2 field, that certainly doesn't make any sense. Or you print something like, assignment incompatible. All these just don't make any sense. So this is something you can take a look yourself. If you look at pretty much every float type has been implemented like this. Okay? You check to see whether 2 objects have the compatible types. Whenever one of them is error, we're going to say yes. Okay? It's just, you can take a look yourself. Now, you might ask me, we have done attributed grammar. How is that relevant? Even though we are not asking you to do it formally, we're not saying, hey, you need to implement a type checker. In the first step, please formalize your type checking process using attributed grammar. You have to submit that, will be marked, then you have to submit implementation. Okay? So here you can do it formally, informally is up to you. Okay? The reason we're not doing that is because it's pretty much very simple. However, if you want to formalize the process, using the example you saw, it's very simple. And let's say we want to write down the rules just for the division operator. This is a type rule. Okay? So it just basically says that E1 is built in terms of E2 and E3. So how do we know the type for E1? It says, firstly, you find the type for is 2 operands. Okay? E1 has the type of float if and only if those operands have the float type. Okay? Then if one of them is integer, then you get integer. Otherwise, if it's not any of those, you get error type. It's pretty much, you can use attribute grammar to formally specify how the type checking can be done formally if you want to. So assignment 4, as I said, I'm going to release specification tomorrow. Essentially you could say two passes or two phases or whatever. So one is identification implemented for you in the part of the starter code. Type checking, something you have to do. Okay? So add I to F. You look at the specification, you know what that means. We'll come back to here. I want to show you. You might also see something. I don't know whether you can see it or not. It's pretty small there. But if you look at this tree, that's the tree decorated by the type checker. I mean, as you can see, all the operators the overloading has been resolved. You see the bottom multiplication because the two operands have time integer. And the type checker has to resolve that multiplication to be an integer multiplication. Therefore, you see I times. For the F class, because the left operand has a type integer, the right operand is the two small. So this is the pass tree. So this see, this is our example. So this is the pass tree. It might be small. I don't know whether you can see it or not. It's pretty small there. But if you look at this tree, that's the tree decorated by the type checker. I mean, as you can see, all the operators the overloading has been resolved. You see the bottom multiplication because the two operands have time integer, and the type checker has to resolve that multiplication to be an integer multiplication. Therefore, you see I times. For the F class, because the left operand has a type integer, the right operand has the type of float. So the entire binary expression has a type of float. So we need to resolve that by changing plus to F class. And you might also see something like I to F. That's because if the left operand is type integer, the right operand is type of float, we need to add a type of coercion operator to convert that integer into a floating point value, so that eventually both operands will have the same type. Why are we doing that? Because eventually we're going to translate VC programs into Java, pretty much Java bytecode. When we translate this into Java bytecode, you have to generate explicitly an I to F instruction to convert the integer value into a floating point value. Then you can issue a floating point addition. Otherwise, JVM is going to crash because two operands do not have the same type. So that's why explicit type coercion has to be done. So we do that by explicitly modifying that part of the tree. You can change that in 3 lines. The code is given in the specification. I just want to highlight that. Okay, so type checking, you're going to add all this actually explaining the specification. You're going to resolve of overloaded operators, turn each of them into a non-overloaded operator. We only have I plus, F plus, we don't have B plus because we don't have a Boolean type. We don't, because it's something I'm going to explain to you when we come back. Because in JVM, even though we have Boolean types, they will be all converted into integer types during the actual implementation. So you only see I, you don't see them. Unless you talk about arrays. You have an array of Booleans, then they will be represented differently. There's something we're going to talk about after we come back. And also the symbol table. Remember the identification? I use the symbol table for that. Okay. So that is a temporary data structure. You're not supposed to use that. Okay, that's only used by the identification phase. Anything else? Yeah, something I'm going to say. I want to come back and do that. See here, you report error message. It's an incompatible type for equal. That's because here there's incompatible type. Yeah, that's the slide I was trying to explain yesterday. So basically, after the identification, you see all these dashed arrows. Those are the outcomes of running the identification. Pretty much, for example, you have a variable here, it's already linked to its corresponding declaration. So every time you call visit identify, you can follow that pointer to retrieve its corresponding type. Then a simple table sitting at the bottom left corner is only a temporary data structure. You're not supposed to use it because it's going to be thrown away once type checking is done. So this is something you're going to see in specification this weekend. So basically we define all these error messages. So every time you see a error, you're going to go through this list. I can report an error message. They are mostly self-explanatory. So only a few places you have a question you can ask me from the forum. As you can see here, identify undeclared. Every time you have an undeclared identifier, you got to call this guy. Incompatible type for return. You return something that's not compatible to the return type. So all these look at attempt to use array function as a scalar. You have declared like x as array, but you say x plus 1. And you try to use that array as if it is a variable that's not allowed. And all these invalid initializer. Again, we'll give you a lot of small test cases. You're going to see that, well, not a lot of small, those two big ones that contains almost everything. Yeah. So these are the list of error messages you're going to use. That's about it. Any questions? All right. Have we finished the concept assignment? Okay. Yeah. Oh, it's too big. Yeah. If you have time, you should just take the visitor class, implement that better. Because that draw package is just drawing to, it's written very quickly. Because when the tree is big, it doesn't move well. Somebody else might just take that and just make it behave better. Yeah, yeah. And that's why there is a printer package that prints the tree in the ASCII format. You might want to take a look at that. That helps. So, I mean, according to my experience, for a language of this size, that should be sufficient because you don't need to have gigantic test cases. I mean, with a few hundred lines of code. You basically, when you try to do your testing, it's normally helpful try to think about a variety of test cases covering different situations. They don't have to be too long. Yeah. That was written only a few places. You have to question that. And you might also see some. We won't come back because in JVM, even though we have Boolean types, that will be all converted into integer types during the actual implementation. So you only see I, you don't see them. Unless you have to talk about arrays. You have an array of Booleans, then they will be represented differently. There's something we're going to talk about after we come back. And also the symbol table. Remember the identification? I use the symbol table for that. Okay. So that is a temporary data structure. You're not supposed to use that. Okay. That's only used by the identification phase. Anything else? Yeah, something I'm going to say. I want to come back and do that. See here, you report error message. It's saying incompatible type for equal. That's because here there's incompatible type. Yeah, that's the slide I was trying to explain yesterday. So basically, after the identification, you see all these dashed arrows. Those are the outcomes of running the identification. Pretty much, for example, you have a variable here, it's already linked to its corresponding declaration. So every time you call visit identify, you can follow that pointer to retrieve its corresponding type. Then a simple table sitting at the bottom left corner is only a temporary data structure. You're not supposed to use it because it's going to be thrown away once type checking is done. So this is something you're going to see in specification this weekend. So basically we define all these error messages. So every time you see a error, you're going to go through this list. I can report an error message. They are mostly self-explanatory. So only a few places you have a question you can ask me from the forum. As you can see here, identify undeclared. Every time you have an undeclared identifier, you got to call this guy. Incompatible type for return. You return something that's not compatible to the return type. So all these look at attempt to use array function as a scalar. You have declared like x as array, but you say x plus 1. And you try to use that array as if it is a variable that's not allowed. And all these invalid initializer. Again, we'll give you a lot of small test cases. You're going to see that, well, not a lot of small, those two big ones that contains almost everything. Yeah. So these are the list of error messages you're going to use. That's about it. Any questions? All right. Have we finished the process assignment? Okay. Yeah. Oh, it's too big. Yeah. If you have time, you should just take the visitor class, implement that better. Because a draw package is just drawing to, it's written very quickly. Because when the tree is big, it doesn't move well. Somebody else might just take that and just make it behave better. Yeah. Yeah, and that's why there is a printer package that prints the tree in the ASCII format. You might want to take a look at that. That helps too. I mean, according to my experience,